At that midnight moment when the clock struck 12 on October 1, 2025, something extraordinary was happening in the world. The United States government, one of the most powerful and influential state institutions, was officially ceasing its operations. It was not a loud, dramatic shutdown with shouts and the collapse of bureaucratic foundations, but rather a quiet, almost unnoticed process. Like everything connecting the country to its past simply vanished in an instant. At that moment, NASA's website, one of the symbols of human achievement in space exploration, disappeared, becoming inaccessible to users worldwide. Social media, which usually buzzed with news and discussions, suddenly fell silent, as if someone had turned them off with a single click. And just at this moment, when it seemed that the entire civilized world had fallen into silence, a mysterious interstellar visitor named TriAi Atlas appeared in the view of observation windows on an orbiting spacecraft, stationed for continuous space monitoring, at a distance of 30 million kilometers from Earth. It was then, at the most unexpected moment, that it entered the camera's field of view directed toward the sky. Coincidence? Perhaps. But this event became the catalyst for my awakening, my inner awakening to observe what was happening. The time when everything unfolded seemed so perfectly orchestrated that it was hard to believe it was merely a coincidence. It felt as if a script, written by someone from outside, was coming to life right now, in reality. Chaos erupted, bureaucratic, sluggish, as if the entire system was trying to hide something important behind walls of silence or, conversely, prepare for the most significant events. Or perhaps this was the most discreet and successful blackout in the history of modern space exploration. Staying with me through this quiet night, you will embark on an intriguing investigation to ultimately understand what truly happened during those silent October days. Why, during this period, the data collected by our instruments show something unusual, and why this story is important for all humanity. In the first part of our story, we will discuss the very beginning, the closure of the American Space Agency and the mysterious arrival of an enigmatic object. It all starts with a solitary and unsettling fact: the government of the United States officially ceased its activities. This process was not accompanied by loud statements or ceremonial events. There were no shouts of joy or dramatic scenes. It resembled a quiet, almost imperceptible click, a signal that funding had run out, and everything else was to proceed by inertia. Federal agencies, including NASA, halted their work. Websites stopped updating, missions were suspended, and employees were sent on indefinite leave or laid off. The agency that for decades has placed objects on the moon's surface and sent rovers to Mars had, at this very moment, posted a short message on its homepage: NASA is closed due to lack of funding. At the same time, while Washington was experiencing yet another lull amid political and bureaucratic battles, a scene was unfolding in space that could serve as the setting for a science fiction film. Just as NASA's public face fell silent and all its staff went quiet, a unique and extraordinary situation began. Precisely at this same moment, at the most advantageous point for observation, when all systems were calibrated and ready, a new object appeared on orbital cameras, which was later named TriAi Atlas. This object, also registered as C-2025N1, was approaching its closest encounter with the red planet. The calculations were so precise that it seemed as if someone had planned this moment according to a script. It is important to understand what we are dealing with here. TriAi Atlas is not just an ordinary space rock. In early October of this year, scientists and astronomy enthusiasts prepared for an important event, a monitoring campaign scheduled to take place from the 1st to the 7th of the month, utilizing the capabilities of the Mars Express spacecraft orbiting Mars. This orbital craft was specifically designed and equipped to study subtle traces of gas and other characteristics associated with interplanetary objects, and its geometric positioning was perfectly suited for this task. During this period, the team of specialists expected that the comet, which would pass at a very close distance, about 30 million kilometers, from Mars, would provide a unique, unprecedented view and new insights into such celestial bodies. Although 30 million kilometers may seem like a significant distance by Earth standards, in astronomical terms, it is practically within arm's reach. At such a moment, Mars is considerably closer to the interstellar visitor than Earth, which would remain much farther from the object over the next few months. To put it in perspective, if the comet were to approach Earth, it would be at a similarly short distance, considered extremely close in astronomical scales. Thanks to Mars's orbital position, spacecraft on its orbit would be able to capture and study this interstellar object in very high resolution. Equipped with cameras and spectrometers, these spacecraft would have a unique opportunity to observe this event in real time, something previously impossible. This would be the first time in history that humanity could obtain such detailed data about an interstellar visitor so close to a planet that is not our own, Mars. Part 3 of 82. The fact that the comet passed at a relatively close distance was of particular significance, considering planetary astronomy, because such a range, from an observational standpoint, is very rare. This would have been an event that could be called unique, as it offered the opportunity to observe an interstellar object almost up close, so to speak, nearby. And this would have provided a chance to learn much more about its composition, appearance, and behavior. However, at the same time, there were difficulties associated with organizing observations and collecting data. During this critical period, when major events and discoveries were expected, there was an unexpected lull in the activities of observation organizers. Within a very short time frame in astronomical terms, there were what could be described as eclipses in the information and communication chain. During this period, known as the closed mode or quiet period, the National Aeronautics and Space Administration, better known as NASA, suspended most of its public operations aimed at informing the public and the broader community. The agency's websites stopped being updated regularly, news was hardly published, and broadcasts from NASA TV disappeared from the airwaves. The entire system of press releases and informational messages was halted, and social media reports were turned off. The equipment that usually provided stunning images and updates on current missions and research on a daily basis also stopped. Only actions necessary to ensure safety, protect lives, and preserve property continued. That is, only the so-called accepted operations, vital for the functioning and stability of space objects and systems, such as the International Space Station, which continued to operate, and critically important satellites, which maintained their work. But for ordinary people observing space, all of this was essentially frozen, and they could not see or understand what was really happening. This was not due to malicious activity. It was a manifestation of political will enshrined in the law on federal appropriations and funding for space programs. However, the effect of this was obvious. It was as if the lights had been turned off in a vast room. Something unusual, important, and very interesting was happening in our cosmic yard, and it was difficult to observe. So why then, this time, do we hear? It seems more mysterious and uncertain than it appears at first glance. Uncertainty and fog in the information leave room for various guesses and assumptions, which, as you will soon see, became the main factor filling the void during those calm October days. Allow me to present a clear and precise timeline so you can follow the sequence of events and understand how everything actually unfolded. Let's start with July 1, 1925, the day when observations were officially announced. On this day, the approach of the comet was recorded, its trajectory was calculated in detail, and astronomers gained an understanding of what exactly was at their disposal. Next, from October 1 to October 7, the so-called window for Martian observations. These were the most favorable days for conducting research from the orbit of Mars. During this period, scientific instruments could operate at maximum efficiency to collect data and make observations. Then, from October 29 to October 30, an important event occurred. Perihelion, the moment when the comet reached its closest point to the Sun. During this period, it was at its maximum proximity to the bright star, making it particularly noticeable and interesting for study. After that, from the end of November through December, the comet reappeared for Earth observers, becoming visible again after passing through the solar conjunction. At the same time, during the period when observations from Mars orbit were most accessible, so-called Martian window, spacecraft and telescopes near the planet had the opportunity to gather maximum information about the interstellar visitor. However, precisely during these days, when this unique opportunity was most relevant, NASA officials chose to remain silent. Internal bureaucratic circumstances related to information management proved to be stronger than the desire to share news with the public. Rumors and speculation began to circulate online, suggesting that something was happening and that perhaps not everything was as transparent as one would like. Reports emerged that almost immediately after active observations began, problems arose. Claims appeared that images had gone missing, telemetry data had disappeared, and the frames that were published suddenly vanished or were edited. There was also talk of unpredictable and unplanned maneuvers by the spacecraft. These events created a wave of noise and speculation amid an information vacuum. But among this chaos, more serious questions arose. Were there indeed significant gaps in the data, or was everything simply a matter of communication failures and explanations of what was happening? This is the main question we will attempt to answer clearly and thoughtfully. We will trace documentary evidence, study spacecraft logs, and apply our knowledge of orbital mechanics to understand what truly transpired. We will try to determine whether the silence was a coincidence or if deeper reasons lay behind it. Because, after all, if someone wanted to observe this object in space without public attention, it would be precisely during those moments when governments and organizations temporarily cease active communications that a great opportunity arises to hide significant events. This is not necessarily related to conspiracies or malicious plans, rather, it is connected to political and bureaucratic mechanisms that have long existed to keep certain information secret during periods of funding and resource interruptions. The question is not whether these mechanisms were used, they were. The real question is, what exactly was happening during those days when these mechanisms were operating at full capacity, and did what we observed match what was officially announced? Was it simply a random malfunction or coincidence? Or was everything happening in strict accordance with a pre-planned strategy kept hidden from the public? It can be said that the orbiter, a relatively recent arrival on Mars, possesses a unique system of color and stereoscopic surface visualization, as well as a set of nomad spectrometers. This suite of instruments allows for detailed imaging of the planet, surface analysis, and atmospheric composition studies. On the American side, NASA is responsible for operating this spacecraft, which also controls the Martian Reconnaissance Orbiter equipped with a phenomenal high-resolution altitude camera, possibly the most powerful of all telescopic systems ever sent to another planet. This camera can capture minute surface details of Mars with high precision, making it an indispensable tool for scientific research. Additionally, NASA has another important instrument, the MAVEN mission, designed to study the Martian atmosphere and the processes of volatile substance evolution. This satellite is equipped with sensitive instruments capable of detecting features of solar wind and plasma flows interacting with the upper layers of the Martian atmosphere. Thanks to these tools, scientists can gather valuable information about atmospheric dynamics and how they change under solar activity. At first glance, the scientific program also includes the rovers Perseverance and Curiosity. These robots are not intended for observing celestial objects like comets. However, they could theoretically capture wide-angle images of the sky or take photographs if given the appropriate command. In case of necessity, these rovers could use their cameras to photograph the surrounding space, should such a command be issued, thus expanding the scope of scientific investigations. The European Space Agency, in turn, has announced plans to observe the space object. They officially declared the launch of an observational campaign scheduled to begin on October 1st and continue until the 7th of this month. Part 6 of 82. These events are timed to the upcoming close approach of the comet to Earth, which is expected to be approximately 30 million kilometers away, and will occur on October 3rd. The main goal of this campaign was to obtain detailed data on the shape and structure of the comet, as well as to measure its activity level. Specifically, it was planned to record spectra capable of shedding light on the comet's chemical composition, which could significantly expand our understanding of its nature and origin. These plans were not kept secret and were widely discussed within the scientific community and covered in open sources. Scientists involved in this observational mission of the European Space Agency gave interviews to Space.com, in which they detailed their plans and capabilities. They discussed the challenges related to observation geometry, as the weak signal and large distances create certain difficulties in data collection. At the same time, their enthusiasm and excitement about studying the interstellar visitor were evident. After all, this was a rare opportunity to study an object coming from interstellar space. This is a standard part of scientific missions, and such a public aspect is an important component of space agencies' activities, demonstrating their transparency and commitment to scientific openness. Regarding NASA's stance during this period, it was different, though not ominous. Public documents, such as the Continuity Plan, which is publicly accessible, clearly indicated that satellite operations continue even during periods when funding or official reports are temporarily suspended. Such a document confirms that the operations of spacecraft, including those orbiting Mars, do not cease entirely. Breaks are related to the need to protect equipment and ensure safety in case of unforeseen situations. This is a fully legitimate and standard approach, provided for by rules and protocols for spacecraft management. In practice, this means that Martian orbiters remain operational, and operators and controllers continue to monitor their status. If necessary, for example, to prevent collisions with space debris or to adjust trajectories, engine burns may be performed. Lowe is an astronomer working at Harvard who has long been particularly active in supporting the idea that the object known as Oumuamua could very well be of artificial origin. His interest in this mysterious cosmic structure is understandable. He was one of the most enthusiastic proponents of the hypothesis that this interstellar object might have extraterrestrial origins. His scientific record includes numerous initiatives related to conducting intensive and often aggressive observational campaigns aimed at thoroughly studying potential interstellar guests. However, despite numerous attempts to detect and record signs of artificial origin, expectations and actual evidence remain entirely different things. In other words, it can be confidently stated that the desire to find proof is one thing, and obtaining it is quite another. It is important to discuss the very possibility of the existence of such extraterrestrial objects, as this question holds the key to understanding what is actually possible in our universe. Now, let's turn to the techniques and science that enable us to make such important conclusions. For example, there is a method called HiRISE, a scientific experiment related to high-resolution visualization, which uses very powerful cameras capable of capturing details with great precision. On the scale of spacecraft, this is considered an incredibly advanced tool. With these cameras, it is possible to record the surface of planets and other celestial bodies with a resolution that allows us to see objects as small as 30 centimeters across from orbit. However, it is important to remember that when dealing with objects located at very great distances, such as around 30 million kilometers, the camera's resolution significantly deteriorates. At such distances, it drops to approximately 30 kilometers per pixel, and this is assuming ideal shooting conditions, which is practically impossible in reality. Smaller objects, such as a comet's nucleus or minor surface features, can no longer be resolved. As a result, we will not obtain a clear image of them, but we can perform photometric measurements. That is, determine how bright an object is and how its brightness changes over time. These measurements provide us with valuable information. For example, we can detect asymmetries in the coma, the cloud of gas and dust surrounding the comet's nucleus. By collecting such data, we can generate a brightness variation curve, which helps us understand the shape and structure of this celestial body. This is not just a technical curiosity but a very valuable scientific method. Using it, we can gather information about the shape of the comet, determine how it rotates, and how matter is distributed around the nucleus. In this case, we are talking about quite significant data, as they allow scientists to better understand the internal structure and dynamics of this object. However, it should be emphasized that close-up imaging, when we want to examine the tiniest details, is a completely different matter. With comets, especially when they are so close to the Sun, observations become more complicated. That is why observing a trio of such objects from Earth was an extremely challenging task. The problem was that the comet appeared in the sky very close to the Sun, a factor that significantly complicated observations because solar glare and the brightness of celestial objects hinder precise detection and monitoring. Astronomers had to exercise extreme caution when aiming their instruments near a bright celestial body to avoid damaging sensitive equipment, as well as to prevent strong glare and light pollution. Under such conditions, especially during twilight or when using high-altitude observatories, observations were possible, though very challenging. Therefore, in these circumstances, observations conducted from spacecraft located on Mars gained particular value, precisely because they allowed, from a different perspective and angle, to observe the comet without battling solar glare. Their positioning and observational geometry provided them with a significant advantage, enabling them to obtain clearer information about the comet even with incomplete data. Regarding what would be necessary to acquire more accurate and comprehensive data, primarily in early October, Mars was in a favorable position. Data received from various spacecraft and systems are often stored and recorded as they arrive, especially when dealing with critically important information related to safety. Such safety-related data are typically prioritized for storage and updates, as they are directly relevant to preventing potential threats and maintaining process integrity. However, when it comes to scientific data obtained during research, such as observations of Mars or other objects, the situation is often much more complex and ambiguous. As of October 1, for example, no official press releases from NASA had been published that detailed the results from Mars rovers, orbital satellites, or observations made by spacecraft like the astrophysical systems or rovers gathering surface or atmospheric data. This raises certain questions. Does it seem suspicious? Is something being concealed or delayed? Nevertheless, there is no need to immediately interpret this as something suspicious or dangerous. It is quite possible that such publications are simply in the process of preparation and will be announced soon. This is quite natural, as processing and preparing scientific results for publication takes time, especially when dealing with complex and voluminous data. Under normal conditions, even without any emergencies, preparing scientific reports, verifying, editing, and subsequently publishing them takes a considerable amount of time. And when a pause or halt occurs, such as during technical maintenance or scheduled interdepartmental breaks, the flow of data that usually arrives and is published is completely interrupted. At that moment, the received data may reside on servers, awaiting scientists to return to their workstations to continue analysis. Perhaps these data are simply waiting for the necessary funding to resume so they can be processed and published, or maybe the observations were conducted but the results were not impressive or interesting enough to publish immediately. In the worst case, they may have been collected, but nothing significant was found in them. Without official confirmation or statements, leaving the situation in uncertainty relies only on assumptions and guesses. However, there are some points that can be identified with a certain degree of confidence. For example, the European Space Agency, ESA, openly announced its attempts to observe the comet during the period when a window for such observations from Mars orbit was available. At the same time, NASA's assets intended for observation and safety continued to operate, and safety and monitoring operations proceeded without interruption during the closure. However, public communications from NASA were suspended, which is related to internal policies and possibly internal orders or restrictions due to regulation. This creates a certain contradiction or discrepancy in the narrative of the situation. Messages from Europe indicated plans and intentions, while from America there was almost nothing. Not because NASA scientists were not interested or did not try to do something, but because the entire public communication system was literally turned off, disabled, or suspended. This silence, combined with the extraordinary nature of what was happening, the appearance of an interstellar visitor on Mars at a time when government activities were halted, created ideal conditions for the emergence of various speculation, rumors, and conjectures. They began to spread actively in many directions, which we intend to further explore. After all, when official sources stop speaking, an informational vacuum is filled with unofficial rumors and assumptions. The question arises: does this noise contain a signal about something important, or is it merely echoes of anxiety and concern caused by the lack of reliable data? Perhaps the silence conceals real gaps and deficiencies in the collected information that could be accessible to the public, or maybe it is simply a normal reaction of the system to temporary disconnection and restricted access. This will be the subject of further investigation. In the third part of our discussion, we will talk about data gaps, information editing, and the NASA homepage at nasa.gov, which in this case displays only a notice of temporary closure and also reports the cessation of updates to pages dedicated to specific missions. As a result, all sections related to particular programs, projects, or expeditions cease to receive new information and updates. Images that are usually automatically loaded from orbital spacecraft orbiting Mars or from rovers also cease to update and turn into static, motionless pictures. In turn, the latest news feeds and information streams related to space events seem to freeze, not being refreshed. Social media platforms where fresh posts and news were previously published also fall silent, and new posts do not appear. All of these phenomena are documented in NASA's official funding and activity plan, which is publicly accessible. This document clearly states that citizens and interested parties will not be able to access many of the agency's web services and information resources during such a pause. However, there is no need to pay special attention to this, as such measures are a normal part of the organization's policy. If, in the first weeks of October, you visited NASA's official website and noticed that the data there was not being updated, it would not be evidence of any secret information suppression. Rather, it confirms that the implemented policy involves a temporary halt in publications and updates. Therefore, the absence of new data is not a sign that something is being hidden or that something unusual is happening. It is more a strict adherence to established rules and procedures. However, this is also when the most interesting developments begin. Not all space agencies worldwide shut down their information resources. For example, the European Space Agency continued to operate normally, and all its services and divisions functioned without interruption. Independent international sources, such as specialized space websites like space.com, a private media outlet, continued publishing news and articles about space flights and research. Astronomical communities and enthusiasts also did not cease their observations and shared new discoveries. Satellite trackers monitoring the orbital parameters of various spacecraft continued updating their databases, providing current information about satellite movements and orbits. All of this indicated that active information activity was ongoing worldwide, and there was no absolute dead zone. This situation was characteristic specifically of the United States and their national space agency, NASA. In contrast, European and other international sources continued actively publishing news, discussing new maps and plans related to Mars exploration and other celestial objects. While official American sources remained silent, creating a certain asymmetry in the flow of information. It seemed as if something was being concealed, although in reality, the reason lay in bureaucratic processes regulating the publication of information. Ultimately, it created the impression that data was being concealed, but in reality, it was simply a consequence of procedures prescribed by internal regulations and had nothing to do with intentional secrecy. Now, it is worth discussing what such a significant gap actually represents. Something more serious than just a temporary shutdown or a planned pause in system operations. Examples include situations where scheduled images intended for publication at specific times never appeared. They were prepared but, for some reason, never made available to the public. Or telemetry data that was supposed to be transmitted from spacecraft and monitoring systems turned out to be incomplete or had timestamps that did not match expectations. Additionally, observations scheduled for specific time windows indicated in scientific charts were never realized in the form of data or images. Meanwhile, files with spacecraft trajectories appeared in systems but lacked explanations or comments in operation logs. All of this serves as red flags, signs that something is happening beyond the standard procedures. It is important to clearly and unequivocally state the existence of this idea because, once the topic of secret space data arises, the discussion tends to become particularly lively and self-sustaining. People tend to assume that behind this lies some dramatic discovery or sensational secret. However, the absence of concrete evidence confirming the classification of certain information does not, in itself, mean that it is secret. Such a lack of evidence merely indicates that we are not dealing with formal government or international secrets, but rather with unofficial silence surrounding certain data. Nevertheless, this assumption was made immediately and loudly, and many people began actively sharing their opinions and statements. Within a few days of the suspension of some projects and services dedicated to studying unidentified anomalous phenomena and the so-called UAP, numerous channels appeared on YouTube, almost instantly beginning to publish their materials. These videos and articles, often based on rumors and unconfirmed data, attracted the attention of a broad audience. At the same time, on popular forums such as Reddit, numerous posts and claims from users seeking to share their findings or hypotheses emerge. Some community members claimed to have found raw image files from Mars obtained from reconnaissance orbiters, which were briefly uploaded to server archives and then disappeared. Others, however, insisted that FITS files, which are the standard format for storing and exchanging astronomical data, contain signs of editing or interference detected through careful pixel-level analysis. Some users continued to claim that the observed spacecraft in these data performed unplanned maneuvers during a specific observation window, and that telemetry data recorded anomalies that could not be explained in public documentation or official reports. However, all these claims should be regarded as unconfirmed and preliminary. They are not proof, but rather part of public discourse and perception formation during a period when information is uncertain and awaiting clarification. It is important to remember that online statements, even if seemingly convincing, cannot serve as a basis for definitive conclusions. They are hypotheses, assumptions, and guesses that require further verification and confirmation. So, the question arises: how to determine what truly constitutes reliable information and what are merely misinterpretations or fabrications? How to distinguish real anomalies from misunderstandings or unfounded conjectures? Here is a simplified checklist that can be used once the planned data are finally published and available for analysis. The first step is to verify timestamps. It is necessary to ensure that the time when observations or images were taken matches the scheduled observation windows, which were communicated in advance by ESA and other organizations. For example, if images or spectrometric data were supposed to be obtained on a specific day, say October 3rd, during maximum approach or another significant astronomical event, and these materials appeared much later or without an exact date, this raises suspicion. If the timestamps on the files differ or are missing, it is a warning sign that warrants special attention. The second point is to analyze the metadata accompanying each observation. This typically includes information about instrument settings, which filters were used, what exposure was set, how the equipment was configured. If observations were conducted by multiple specialists or on different instruments, and the results match, this serves as a good cross-check. Conversely, if one observer records something drastically different from the others, it is a red flag that requires more detailed analysis. The third aspect involves cross-verifying the data with open and publicly accessible resources from the European Space Agency and other international organizations. Part 13 of 82. When the results from missions such as Mars Express or data from ExoMars programs are published, this fact immediately sets certain boundaries and shapes expectations. It is not realistic to expect real-time updates on the comet's status or new data about it. One should not anticipate the usual speed and regularity of publications that typically accompany astronomical discoveries or research. Instead, it is necessary to prepare for the fact that new information about the comet will appear only after a specific stage of funding has been completed or relevant resources have been obtained. This is quite natural. It would be entirely abnormal if, months after the so-called shutdown, we still had no new data about the Mars observation window, despite NASA having clear capabilities and technical means to obtain such information. Such a scenario would imply either that observations were not conducted at all, which would be a missed scientific opportunity, or that the data exists but is being kept secret for some reason, raising questions and requiring explanations. I want to emphasize and support those who are cautious about the current situation and do not rush to accept all statements at face value. Let us note that the comet passes through the so-called solar conjunction with Earth at the end of October and in November. During this period, observing the object with ground-based telescopes becomes difficult or impossible because sunlight interferes with its visual detection. In late November and December, the comet reappears, becoming accessible for observation. This reappearance provides an opportunity to verify any claims about unusual behavior of the comet made during that observation window associated with Mars. If someone claims that in early October the comet exhibited strange properties, suddenly revived, or its spectral characteristics changed, or it altered its trajectory, these effects should leave noticeable traces, continue to manifest, and be observable even after the conjunction with the Sun. Data collected after this period can confirm or refute such hypotheses. Patience and careful attention to detail are essential to obtain answers that exclude speculation and conjecture. This is exactly where our current observation stands. It can be confidently stated that the so-called dead zone existed, and this truth is widely recognized without dispute. An important fact is that NASA's communications during the period when Mars observation was at its maximum were suspended, due to the closure of relevant programs or laboratories. This is documented and beyond doubt. Public statements claiming that data disappeared, was falsified, or simply does not exist also occurred. Such events happened, and they became part of the cultural and informational background surrounding this event. However, it is important to emphasize that in the early stages of October, no verified evidence was provided to confirm data concealment. Mostly, the gaps in information we observe are related to political or administrative decisions. The question of whether there are any real anomalies hidden behind these informational voids, underneath the political veneer, is something we can only understand once all data transmission channels are reopened and regular releases of new results begin. Until then, the dead zone remains essentially a silent, irritating, and incomprehensible segment of the timeline. It may be entirely harmless, or it may conceal something significant that warrants further examination. And it is this uncertainty that fuels people's desire to ask questions. The next logical question in such a situation is the comet behaving unusually? Or are all these discussions just noise around a normal astronomical phenomenon? Let's try to analyze this by looking at the mathematical aspect of the issue, at its trajectory, because it is here that guesses, hypotheses, and precise calculations intersect. Despite all rumors and assumptions, orbital calculations can reveal a lot about the actual state of affairs. Let's start with the fact that the comet's trajectory is a hyperbola, which is an important and key detail. A hyperbolic orbit means that the object is not gravitationally bound to the Sun in the traditional sense but is moving along a hyperbolic path. The recently observed comet appears to have arrived from the depths of interstellar space. This unusual visitor orbits our star as if it were an invisible traveler making its way along a complex and precise orbital path. However, unlike typical comets belonging to our solar system, it is heading back into the depths of interstellar emptiness and will never return to our horizons. The orbital parameters of this celestial body determine its position in space, with the so-called perihelion, the point on the orbit closest to the Sun, being particularly significant. According to the latest calculations, this point is expected to be around October 29 or 30 of the year 2025, that is, at the end of October next year. The distance to the Sun at that moment will be slightly more than 1.36 astronomical units, slightly exceeding Earth's average distance from the Sun. This result has been obtained through careful analysis of the orbital characteristics and confirmed by a group of specialists from the Solar System Dynamics Center, part of the JPL Space Laboratory. This is exactly how orbital calculations and modeling are performed in practical astronomy. When it comes to precise measurements of the comet's position, not only the specific point matters but also the processes through which astronomers arrive at accurate data. Observers around the world, both professional observatories and amateurs, record the position of this object against the fixed star fields. Each such observation contains important information, coordinates that can be expressed as right ascension and declination, that is, celestial latitude and longitude, as well as the exact time corresponding to the moment of observation. These data are collected in large volumes, sometimes hundreds or even thousands, and all of them allow tracking the comet's movement across the sky. Afterwards, specialists use mathematical models to fit the orbit, creating a calculated curve that can predict the object's position at any given time based on gravitational laws, primarily the Sun's gravitational pull. When predictions match actual observations, it can be confidently said that the orbit is accurately determined. In cases where discrepancies, so-called residuals, occur, scientists investigate the causes. Sometimes these are measurement errors, other times, they are due to forces acting on the object that are not gravitational. Comets are characterized by non-gravitational forces, which often significantly influence their motion. When the comet's nucleus heats up under the sun's influence, sublimation occurs, the transformation of ice directly into gas. This outflow of gas, escaping from the nucleus, carries momentum with it, creating an effect similar to a small rocket engine. As a result, the comet's nucleus sometimes experiences unexpected changes in trajectory, especially if active regions are located in specific areas or if the comet rotates at different speeds. In such cases, the orbit must be adjusted by introducing additional parameters, so-called non-gravitational parameters, into the model. These account for the thrust generated by gas and dust emissions, an effect that may be very small but becomes noticeable over long-term observations. In practice, such parameters help explain shifts in the comet's position amounting to several arcseconds over months of monitoring. Regarding the specific comet temporarily named 3IATLAS, by early October, scientists already had important data obtained by the Hubble Space Telescope in July of that year. These images helped determine the size of the nucleus and confirmed the presence of active dust formation processes. The upper limit of the nucleus radius was established based on these observations, and a bright developing tail region was also identified, indicating that the nucleus is sufficiently warm and volatile to release gas and dust. All of this confirms that a comet is not just an inanimate rock but an object with active processes driven by solar heat. However, among the data obtained, if we imagine a situation where a comet suddenly begins to accelerate at a speed that cannot be explained by the influence of solar gravity or simple gas emission, then we would certainly notice drastic changes in its motion, primarily in the Doppler shift. The essence of this phenomenon is that if it were found that the comet unexpectedly accelerates, we would observe significant, albeit temporary, shifts in the spectral lines indicating a change in velocity. Similarly, if we carefully track the position of this celestial body using high-precision instruments, we would notice that it is not located where our gravitational model, based on known laws and data about the solar system, predicts. As a result, with the help of space telescopes and radar observations, even very small positional changes, equivalent to accelerations of fractions of a millimeter per second per day or week, can be detected. These measurements are incredibly sensitive and allow us to record even the slightest anomalies in the movement of celestial objects. As of early October, all publicly available orbital solutions for asteroids and comets, including the object designated as 3IATLAS Atlas, do not indicate any unexpected or strong accelerations. Recent measurements made with orbital instruments show that the behavior of this celestial body is consistent with ordinary gravitational effects and moderate non-gravitational forces caused by gas emission during its active phase, an occurrence observed in many comets. Its orbit remains hyperbolic, meaning it will continue its journey, leaving the boundaries of the solar system, and no signs have been found that it will suddenly deviate onto some related orbit or be ejected from the system faster than physical laws predict. Could there be extremely subtle anomalies that have not yet been published? Certainly, such cases are possible. Science is constantly evolving, and the accuracy of orbital models is continually improving. As new observations are received, especially after additional observation points, such as when the object emerges again from conjunction with the Sun and its orbit becomes clearer, these data will be updated. If new measurements reveal any unusual nuances previously unnoticed or hidden in preliminary data, we will certainly learn about them from published and official orbital elements. The Center for Planet and Asteroid Research, along with organizations like NASA through the Johns Hopkins Space Center, regularly publish updates on the orbits and characteristics of celestial bodies, and their data are accessible to the public. Anyone interested can independently verify the latest information and confirm its accuracy. It is also worth noting that the European space program, carried out with the help of Martian orbital stations, such as Mars Express and the ExoMars mission, conducts observations aimed at detecting indirect signs of the shape and structural features of objects orbiting or near Mars. Although their cameras, even under optimal conditions, are unable to resolve the tiniest details of a comet or asteroid's core from 30 million kilometers away, they can record changes in brightness over time. These brightness variations can reveal much about the rotation state, shape, and structural characteristics of the object. For example, if a comet's nucleus is elongated or tumbling through space, periodic changes in its brightness would indicate this. Similarly, if the coma surrounding the nucleus exhibits asymmetry, it is likely that one side is brighter due to localized activity, such as gas or dust jets, that produce transient signals varying over time. Such observations enable the detection of non-gravitational effects or structural features, but only after careful analysis of the collected data. As of the end of last week, the results of such observations provided by the European Space Agency are available. Considering these statements in a context that extends beyond mere assumptions and hypotheses, it is important to remember that without convincing evidence, such claims remain unfounded speculation. I mention them precisely because they have entered the realm of cultural and scientific discussion, not because they are confirmed by rigorous research or verification. If the jets ejecting gaseous substances truly generated small acceleration impulses, a logical question arises. Where exactly could these jets appear, strictly according to physical laws? Would such phenomena fit into existing orbital models, or could their presence be detected through visual observations? Ultimately, a bright jet directed from only one side of the nucleus would lead to noticeable asymmetry. This effect is generally easy to detect through spectroscopic analysis, which can determine the composition of the jet's substances. These could include water, carbon monoxide, methane, or other volatile components. Indeed, ground-based observers obtained spectra of 3 objects known as ATLAS in July and August, and these spectra displayed features characteristic of typical comets releasing volatile substances. If something fundamentally different had been discovered in October, scientific papers, at least preprints, discussing such unusual findings would likely already be appearing. However, as of early October, no such publications have been registered. This allows us to draw an initial conclusion. At the moment, the comet is behaving as expected, exhibiting typical signs of cometary activity. This is the fact I can confirm for you. After the observations of conjunctions and interplanetary alignments are completed at the end of November, as well as after receiving data from Mars, new results are planned to be published and the orbital parameters will be reviewed. Specialists from the main planetary center will update their models and calculations, and the Johns Hopkins Space Flight Center, JPL, team will update the Horizon database. If during October's observations any unexpected changes in the object's position or velocity occur, the corresponding updates will certainly reflect that. If the object's mass turns out to be significantly different from previous estimates, this will also be evident from the revised calculations. If spectroscopic studies reveal something unusual or strange, such data will undoubtedly be published and discussed. Science is a slow and transparent process. It takes time to acquire and verify new data. In the coming months, we will receive answers that will allow us to compare current assertions with new facts. This will be our test. If the anomalies currently discussed truly exist, there will be traces that will pass expert scrutiny and remain convincing to the scientific community. If, on the other hand, these anomalies turn out to be errors or random fluctuations, the updated data will show that, at best, in the most dull but reliable form. So, the current conservative approach is as follows. Existing measurements based on September data fully support the interpretation that the object is a regular comet with typical activity levels. The orbit we assume is hyperbolic, which aligns with the hypothesis of an interstellar origin of this body, adding a certain intriguing mystery. At the same time, claims of strange dynamics, unexpected acceleration, or unusual signals related to this object remain unconfirmed to date and have not been validated by peer-reviewed scientific literature. This does not mean that nothing interesting has happened or that mysteries have disappeared. On the contrary, it indicates that we currently lack sufficient evidence to make definitive conclusions or statements. This uncertainty leads us to the next level of reflection and hypothesis. After all, if the dynamic characteristics of the object are not a critical point for understanding its nature, then perhaps it is more important to consider its composition and structure. This range, encompassing the comet's nucleus, reaches approximately 17,000 kilometers in diameter, a size that surprises and prompts reflection. No known object in our solar system has exhibited such a scale. However, it should be clarified from the outset that we are talking about a certain range of estimates, as determining precise parameters is very difficult. Such a broad range is due to the fact that, ultimately, we cannot directly measure the size of the comet's nucleus because it is too far away, and the observations we have are only images and spectral data. So, what exactly do we observe with telescopes like Hubble? Usually, it is not the nucleus in the full sense of the word, but rather its surrounding cloud, a dense accumulation of dust, gas, and cosmic particles that appears as a coma. This coma is a complex nebula filled with tiny particles and gas, and it is what shapes our image of the object. Therefore, scientists have to use inverse analysis, trying to draw conclusions about the nucleus itself based on the data obtained. To determine its size, it is necessary to assume how light reflects off the surface of the comet, how reflective it is, meaning, what its albedo is, as well as to consider the efficiency of dust and gas ejection. These parameters generally vary depending on conditions and hypotheses, so different assumptions can lead to different results. Suppose we assume that the comet's surface reflects sunlight in a certain way, and based on that, we infer its size. However, since these parameters remain not entirely clear, the final estimates of the diameter can differ significantly. The team of scientists using the Hubble telescope also estimated how quickly the comet loses mass. That is, how much material is carried away into space per unit of time. These estimates are based on models assuming that, over a period roughly equal to 1 July, the comet ejects between 6 and 60 kilograms of dust and gas into space every second. Again, the range is very broad because the exact distribution of dust particle sizes and other parameters can significantly influence the results. This active outgassing is a characteristic feature of comets, especially as they approach the Sun. During this approach, comets begin to lose mass, and it is this process that makes them visible to us. The released gas and dust, reflecting sunlight, create a bright envelope that is perceived as a glow. As a result, the comet becomes noticeable due to gases and dust particles erupting from its nucleus, brightly illuminated by the sun's rays and causing fluorescence. The widely accepted interpretation, based on numerous publications and preliminary studies, suggests that the object called TriAi Atlas is indeed a comet. It has a nucleus composed of a mixture of ice and rocky materials, as well as active gas emission processes. All of this is typical for comets. They behave as expected, showing characteristic signs of activity. However, data obtained from the Hubble telescope raises questions. Perhaps there is something more complex or unusual that requires a different explanation. However, at present most scientists tend to believe that these observations confirm that the 3IATLAS Atlas is indeed a comet. Nevertheless, there are also speculative hypotheses that make the situation particularly acute. In some less formal sources, as well as in interviews with journalists, estimates of the mass of this object reaching tens of billions of tons have been discussed. It is important to emphasize that such estimates significantly exceed what one might expect based on the typical sizes of comet nuclei. For example, if we assume that a comet nucleus has a diameter of a few kilometers and consists of ice and rock with a density of about 500 to 1,000 kilograms per cubic meter, then its mass should be in the range of a billion tons. To reach a figure of tens of billions of tons, one would need to either assume that the nucleus is much larger in size or that it is incredibly dense. If the nucleus is still relatively small, then achieving such a mass would require it to be extraordinarily dense. This phenomenon could indicate the presence of an object formed in a different chemical environment, possibly surrounded by a different star than ours, or it could be a fragment of something that has undergone a differentiation process. Differentiation is a complex and important process in the development of planetary bodies, during which, as a result of internal melting, heavy metals such as iron and nickel separate and settle in the central part of the body, forming a core. When considering the formation of a large object, such as a planet or a massive asteroid, after its formation and differentiation, it can be destroyed as a result of collision or another catastrophe. Such events leave behind nearly pure metal fragments on the surface and in the debris, which can drift freely in space. In our own solar system, similar metallic fragments are found in the form of meteorites, which are remnants of shattered and cooled cores of ancient planets or their leftovers. These meteorites are often rich in metals and serve as valuable samples for studying the history and composition of our system. Could an object, for example, called 3IATLAS, represent an interstellar version of such a metallic fragment? This is quite possible, although it remains a rather speculative assumption, since confirming such a hypothesis requires detailed spectroscopy, an analysis of the light emitted by the object that would confirm its unusual and possibly alien composition. Just think, what if such an object truly is a part of a destroyed body formed around another star, which differentiated and then was shattered? In that case, it could be in interstellar space, traveling between galaxies. Another possibility is that it is the remnants of a star collision or fragments of a supernova. However, this idea is less likely, since such cosmic cataclysms are extremely violent processes in which almost everything nearby is subjected to intense processing or vaporization. As a result, solid particles and metals usually disappear or break down quickly. Therefore, the probability that such an object has survived and reached us as a massive metallic structure is low, although not entirely excluded. And here begins the most interesting part. In science fiction and among experts, there is an idea that this object is not a natural formation at all, but artificial. Imagine some kind of probe or spaceship, or even part of a gigantic, engineered structure. Something deliberately created by intelligent beings in distant space. This scenario literally sparks the imagination, as it implies the existence of technologies beyond our current capabilities and the presence of goals for which such constructions were made. It is no secret that in scientific circles there are many opinions and hypotheses regarding the origin of such objects. In most cases, the detection of elements like nickel or high mass is not considered proof of artificial origin, since such metals are widespread in nature. However, combining these data with uncertainties in mass estimates, questions about composition and origin, as well as the timeframes during which such objects could have formed, creates room for a variety of speculations and hypotheses. If we assume that this object is indeed a dense metallic fragment rich in metals, its strategic value and the implications of such a discovery would be enormous. Even without assuming its artificial origin, such a massive metallic object passing through the inner regions of our solar system would attract great interest from scientists and engineers. It could become a valuable resource for extracting metals, rare and expensive elements necessary for technological development, space exploration, and industry. In the field of space mining, discussions about capturing and utilizing asteroids or large interstellar objects for obtaining metals and other valuable materials are becoming increasingly active. Even if it is not possible to fully capture the object, its hyperbolic trajectory, indicating an interstellar origin, makes it a scientific goldmine. Every instrument aimed at studying or collecting samples would become a crucial tool for expanding our knowledge. Humans are creatures inherently seeking patterns and connections in the surrounding world. It is very important for us to understand how the universe works, and that is why, when official scientific sources or authoritative channels remain silent and do not provide clear explanations, we begin to fill the resulting void ourselves. At such moments, we create our own narratives, trying to understand what is happening based on the available data. In this case, the completion of the main scientific work and the publication of the results created a specific informational void that allowed room for reflections and hypotheses. The nature of the interstellar object recently discovered proved to be particularly unusual and mysterious. Its unique characteristics, such as size and composition, significantly complicated the task of determining its origin and nature as a visitor from interstellar space. The scientific data provided for analysis contain enough raw material to propose more complex and hypothetical ideas than those initially assumed. I do not reject human curiosity and the desire for knowledge. On the contrary, I try to consider everything within the context of existing knowledge and hypotheses. It is important to understand that the questions being asked are not meaningless or illogical. The problem is that, at present, we do not have definitive answers. The lack of conclusive data is precisely why some researchers draw conclusions based on assumptions and hypotheses rather than confirmed facts. In this context, an important question arises. What could disprove the hypothesis of a metallic monster, this unusual interstellar object? What signs or parameters could serve as proof or refutation? First, if subsequent observations confirm that estimates of the size and reflectivity, albedo, of this body decrease to values typical of ordinary comets or asteroids, this would already be a strong argument in favor of its natural, rather than artificial, origin. In that case, the mass of the object would fall within the typical range for known celestial bodies, and the hypothesis of a metallic monster would lose its relevance. Second, spectroscopic studies could significantly clarify its composition. If the analysis shows that the predominant components are ices and typical silica, it would indicate that the object is a regular comet or asteroid, not a metallic body. Such a conclusion would considerably weaken the hypothesis of a metallic shell and possibly point to a natural origin. The third important aspect is the study of the gravitational parameters and the behavior of the object during its movement. If refined measurements of acceleration and deviations correspond to what is expected from water ice or carbon monoxide release, this would strongly confirm its cometary nature. These data would allow for a more accurate understanding of whether this body has active gas emissions or is passive, without signs of life or artificial construction. The fourth aspect involves analyzing the light curves and their variations. If they show that the object behaves like an irregular, fluffy, and very lightweight body with low density, this would clearly indicate its cometary nature. At the same time, if its luminosity remains constant or changes in accordance with a denser and more compact structure, then the hypothesis of a metallic and artificial origin becomes less likely. All these checks are quite feasible tasks that require only high-quality and accurate data. Modern astronomy has the tools and methods to obtain such data. It is only important that they are collected and analyzed. The most important thing for everyone to remember is that the absence of evidence for something is not evidence of absence. To date, we have no definitive confirmation that this interstellar object is an ordinary comet, nor that it is something unusual or artificial. The data obtained with the Hubble telescope are consistent with the hypothesis of a comet, but do not exclude other possibilities. The trajectory of this body indeed resembles the movement of a comet experiencing weak gas emission, which is typical for such objects. So, let me share my perspective and explain how the process of working with and controlling information occurs in large and complex scientific and technological organizations, such as a space agency. I will start with a promise. I will tell you how data production and dissemination are carried out, as well as what happens if new information suddenly appears that could radically change our understanding of the situation, for example, regarding the 3IATLAS Atlas project. In such cases, the agency will review every existing claim and every hypothesis previously made. This applies not only to the hypothesis of a metallic structure, the mass of the objects, and the resource ratios, but also, which is especially inconvenient for some, to the so-called artifact angle. Because this angle could become a subject of debate and doubt, as its accuracy and interpretation can significantly influence assessments and conclusions. Science is an ongoing process of testing and refining hypotheses. It advances precisely through experiments, trials, and continuous verification of ideas, not merely by dismissing or ignoring them. An essential part of this process is the relationship between belief in a theory and the presence of convincing evidence. If, at present, the evidence remains weak and the level of uncertainty is very high, then we are exactly at such a point. This is an honest description of the situation, and that is the essence of scientific progress. Moving forward, even if the path is thorny and slow, even if the result is not yet final and requires further research. Yes, this path can be messy and difficult. It does not always align with our desire for quick answers. But it is through this way that truth, or at least an approximation of it, is achieved, by the consistent accumulation of evidence and the gradual elimination of doubts. Now, to better understand how secrecy and information protection can be ensured under such conditions, it is necessary to discuss who and under what circumstances is capable of keeping secrets, if such secrets even exist. After all, if there are pieces of information that need to be kept confidential, then the mechanism for blocking and concealing them becomes just as important as the motivation to preserve them. It is important to understand how the agency's policies regarding working with secret projects are formed and how reliably control over classified information is maintained. Let's turn to internal mechanisms, because the key to understanding how data management and protection are carried out lies there. First, we should examine how the bureaucratic structure responsible for security and management of secret information functions. This is less dramatic than some conspiracy theories suggest, but nonetheless very effective. Within such a system, there exists a so-called continuity of operations plan in case of sudden failures or cessation of federal funding. This plan is developed and approved by law so that at any moment, even under the most unexpected circumstances, the organization can continue to perform its key functions. The main idea of this plan is the clear definition of personnel categories and their roles, as well as instructions for continuing essential operations. The categories of activities that must be preserved and carried out in emergency situations are very strict. Primarily, these include tasks related to ensuring the safety of life and property. For example, maintaining the operation of the International Space Station is a vital task, and it is carried out even in times of crisis. It is obvious that dispatchers and operators responsible for managing spacecraft are involved because their task is to keep the crew and equipment safe and ensure the system's operability. Satellite operations, especially those designed to protect important assets or infrastructure, are also among the priorities. However, tasks related to communications and informational support are not included within this plan. Updates to informational websites, social media posts, press releases, all of these are usually suspended or completely halted during emergencies. Why? Because in crisis conditions, the main priority becomes preserving the integrity and security of systems and information, rather than publicly demonstrating activities. It can be observed that this approach creates a certain pattern of behavior. In the case of spacecraft launched to Mars or other planets, it means that operational teams can work in autonomous mode to keep the spacecraft safe, even if this is not a secret operation or conspiracy, despite the fact that many perceive such situations exactly that way. In fact, it is a standard administrative procedure that, in its manifestation, produces the same effect: a sense of complete silence and lack of information. Now, let us turn to a more complex and darker aspect of the issue: civil-military interaction, because it is in this sphere that the most mysterious and incomprehensible processes occur. The Ministry of Defense, the National Intelligence Agency, and Air Force laboratories engaged in research on strength and security maintain a constant level of awareness of the situation in space. Their task is to monitor everything happening in orbit, as well as much beyond it. They have both ground-based and space-based optical telescopes, which may surpass in power the most advanced instruments used by NASA-led science. Additionally, they possess radar systems capable of tracking and identifying objects millions of kilometers away from us. At the same time, they rarely publish their observations, which sometimes causes confusion. But this is not something sinister, it is their direct mission. Their goal is to protect space assets, ensure national security, monitor potential threats, and maintain a high level of situational awareness. If 3IATLAS class satellites had passed through the controlled space, and the probability of this was very high, as it was, then observation systems would have detected them. They could have collected optical images, radar profiles, and conducted spectroscopy depending on the type of object. The question of whether this data is shared publicly is almost beyond doubt. The answer is unequivocal: it is almost never published. Is there a possibility that this information is transmitted to NASA scientists? Theoretically, yes, through special secure channels, if scientific or security considerations necessitated it, but such transmissions are not publicized or announced openly. Within interagency cooperation, there is a certain protocol for data exchange, and collaboration between NASA and the Ministry of Defense is standard. In such cases, orbital parameters for satellites and space debris become shared. In the event of a collision threat with a commercial satellite, data flows between agencies intensify to resolve the issue quickly. This cooperation occurs constantly, in everyday operations, and attracts little public attention. And what happens if military personnel observe an unusual phenomenon during their monitoring, such as the appearance of the 3IATLASes? They might gather such important information that they would pass it on to NASA staff, control centers, or security specialists, those involved in mission oversight and safety. However, all communications related to this information remain classified, and are not accessible through public channels. Ultimately, a situation may arise where data exists, decisions are made based on it, but the public and the scientific community remain unaware. Everything happens within the framework of existing legal and regulatory norms, not because something is being deliberately concealed, but because it is provided for by laws and funding. At the same time, the European Space Agency demonstrates a completely different level of transparency. During this period, they continued to operate normally, published news and updates, and scientists gave interviews. When asked about the 3IATLAS, they openly discussed their plans and observation methods. Some of their scientists were even quoted in articles on space.com, creating the impression of open and transparent activity. While Europe appeared as an open book, publishing all its data, America remained in the shadows, silently observing the situation. The reason for this silence was not a desire to hide something or conceal facts, but rather the necessity to comply with laws aimed at combating information shortages and ensuring continuity of plans. Legislation and funding in the United States require a certain level of secrecy and caution, which explains the lack of public announcements. This is the simplest and most understandable explanation of what is happening in this situation, probably the easiest to grasp. However, there is an alternative hypothesis suggesting that the closure is not accidental but serves as a cover-up for hiding information that could be very important. In this case, the closure is not just a technical necessity but a kind of shield that allows concealing from the public or the press certain information that, otherwise, would likely be publicly disclosed or even denied. Nevertheless, to definitively determine which of these scenarios is true, evidence is needed, and we currently lack it. Allow me to explain more clearly and in detail the essence of the law underlying this entire situation, the Deception Prevention Act. It is important to understand it because it forms the legal basis for what is happening. This law was enacted in 1884 and has been amended and supplemented numerous times since. Primarily, it prohibits federal officials from spending or committing to fund any projects, works, or programs unless such expenses have been pre-approved by Congress. Violating this rule is considered a criminal offense, underscoring its strictness and importance. During periods of temporary funding suspension, agencies are forced to take measures to minimize their expenses so as not to exceed allocated funds. In such cases, leaders must determine which activities are permissible and do not violate the law. Firstly, the focus is on tasks related to ensuring the safety of lives and the preservation of property. These are the types of activities that are permitted and officially documented. After that, agencies submit their contingency plans to the Management and Budget Office, which must evaluate and approve their actions. For employees who continue working during periods when funding is suspended, special rules apply. They receive back pay once funding is restored. At the same time, any work or actions carried out without approval and authorization, even in isolated cases, are considered violations of the law. This creates a very serious sense of caution among management and staff. As a result, managers often prefer to send personnel on leave, sometimes generously, to avoid situations where someone might accidentally or intentionally perform prohibited actions. Consequently, even important tasks such as updating the website or informational resources to inform the public about new space discoveries or launches are often not carried out, since such actions are legally considered inadmissible during this pause. Now, let's consider the issue from the perspective of the political and informational environment. The NASA Continuity Plan essentially states in plain language that during the shutdown, the public will not have access to the nasa.gov website or NASA TV channel. This information is clearly indicated on the 7th page of the updated plan for 2024, which is published in PDF format and available for review. The agency warns the public in advance that all these resources will be offline during this period, so when the shutdown occurs, it will no longer be a surprise and will not be perceived as a violation of the law. However, there is one significant problem. Most people do not read official continuity plans, and not only them, but the majority of citizens generally pay no attention to such documents. Imagine a situation where people notice something happening in space, for example, unusual phenomena or signals, and at the same time, NASA remains silent, not providing any information. This creates a gap between the legal procedures and public perception. This gap provides fertile ground for the emergence of various conspiracy theories. If, during a period when something truly important or unusual is happening, such as activity on Mars or around other planets, everyone remains silent, it breeds distrust and suspicion among some members of the public. Especially if these events coincide with the website shutdown or the absence of official messages. In such a situation, the question arises: who makes decisions about what information can or cannot be disclosed, and who determines what should be kept secret? If NASA is suspected of observing anomalous phenomena, this data is the first to be received by the military and intelligence agencies. In today's world, when it comes to space observation and potential mysteries related to unknown objects or phenomena, the chain of decision-making processes plays a crucial role. When military sensors detect something unusual or suspicious, all this information is transmitted through a complex decision-making system that primarily involves defense mechanisms and intelligence structures of the relevant agencies. These mechanisms are usually kept strictly classified, and their contents are closed to the public by default, unless special permission is granted. The general level of secrecy by default implies that neither side discloses internal processes related to analysis and decision-making until there is a necessity or political will for public disclosure. As a result, most decisions regarding potential observations or responses can remain hidden for months or even several years, creating a prolonged period of uncertainty and incomplete information for external observers. The public often does not wish or seek to learn about such internal mechanisms and processes, as they seem complex and often evoke a sense of uncertainty or even distrust. However, the situation changes dramatically if a political authority decides to declassify certain information and publish it for public access. In such cases, there is an opportunity to obtain at least basic initial data that was previously hidden behind a veil of secrecy. It is important to note that the process of such declassification usually does not happen quickly. It can take months or even years, depending on the level of complexity, the need for verification, and political decisions. In practice, if any information about observations by surveillance or intelligence systems appears in the public domain, it indicates that the relevant authorities have deemed such information suitable for public discussion. For example, a recent campaign for observing space objects, which was publicly announced and actively discussed, provides a clear indication of the existence of certain data. Specifically, articles published on space.com on September 28 and October 1 of this year, and interviews with scientists discussing scheduled observations, are vivid examples of such transparency. These materials serve as initial points for understanding the situation and demonstrate transparency in the information exchange process. If the National Aeronautics and Space Administration, that is, NASA, indeed had such plans for observation or reconnaissance, there would certainly be information about them in public sources. However, to this day, as far as is known, no such statements or announcements have been made. There is a certain logic to this. Perhaps all such plans and activities do indeed exist, but for some reason remain behind closed doors because the infrastructure related to these operations is still in a restricted mode. It is quite possible that scientists and specialists involved in these projects would like to share their results or discuss them, but administrative or legal restrictions prevent this. The administration may have a strict observation schedule, but without appropriate public relations services and specially allocated resources for preparing press releases or interviews, such messages and publications simply do not appear. This is not because these events are impossible or legally prohibited, but rather because the mechanism for their dissemination operates in an autonomous mode managed by an internal bureaucratic system. So, what conclusion can be drawn about the internal friction and policies inherent in these government structures? In conditions where NASA operates under strict legal restrictions during lockdowns and emergencies, a situation arises where, even if space operations continue, the public remains unaware. These restrictions essentially force specialists and leaders to keep communication with the public at a minimum, which sometimes creates the impression that the most important information is deliberately hidden to avoid panic or unwanted public attention. At the same time, the civil-military interface, i.e., the interaction between civilian and military structures, often allows the exchange of data that is accessible to internal experts but never seen or known by the general public. Unlike in the modern world of space observation and research, where many tools and methods exist to track objects moving in the depths of space, many aspects remain hidden or inaccessible to the wider public, especially when it comes to secret systems and military technologies. In particular, there is limited information about what specific means are used to observe space objects, especially those beyond Earth's orbit, and about the capabilities of closed intelligence agencies. Let's start with spacecraft orbiting Mars. Among them is a spacecraft from the Chinese National Space Program called TriAN-1. This satellite was launched in February 2020 and has been continuously operating in orbit around Mars since then. Although China's space exploration program is considered less transparent than those of countries like the United States, TriAN-1 has its own peculiarities. In particular, this satellite is equipped with cameras designed to observe the planet and its surroundings. A question often raised by researchers is whether these cameras, operating within the scope of the mission, could have captured the approach or activity of any comet. Providing a definitive answer is difficult, as there are no official statements on this matter. However, it is important to note that the absence of public announcements about observations does not necessarily mean that such observations did not occur. It is quite possible that the Chinese satellite simply did not share this information, or that it remains classified for reasons of national security or strategic interests. In any case, the fact that the cameras are present provides grounds to assume the possibility of obtaining data on space objects, including comets, even if no public disclosure has been made. Moving on to a broader topic, one cannot ignore the activities of the scientific community in planetary sciences, especially concerning the Psyche mission. This mission, launched by NASA in October 2023, is aimed at studying the asteroid numbered 16, Psyche. This asteroid is rich in metals, and its study could provide valuable information about the composition and origins of such bodies. In preparation for the final phase of the flight, scientists and engineers discussed possible scenarios for using the onboard cameras and other instruments. Some studies suggest that during certain periods of the trajectory, in so-called cruise phases, geometric conditions could have been particularly favorable for obtaining reference data or photographs. Specifically, the possibility was discussed that on certain dates, chosen based on the asteroid's geometry and position, the camera might have captured additional surface details or environmental features. However, as far as is known, the final results of these hypotheses have not yet been confirmed, and it remains unknown whether anything of this sort occurred. Although the main Psyche mission focuses on studying the asteroid rather than comets, it is important to remember that spacecraft and satellites in the past have also been used for observations of comets and other interplanetary bodies. Such capabilities, although not their primary purpose, are quite possible and can certainly be implemented given the appropriate instruments and conditions. Nevertheless, nothing currently confirms that such observations actually took place or were recorded. All of this remains speculative, based on logical reasoning and known technical possibilities. Now, let us consider the capabilities of ground-based radar systems, which are often used not only for scientific purposes but also for military and intelligence operations. In particular, there are specialized systems operated by military structures and intelligence agencies capable of tracking objects in space over long distances. The most powerful of these systems is the space radar managed by the United States Space Force. Located at the Kwajalein Base on the Marshall Islands, this radar operates in the S radio band and is designed to monitor satellites, space debris, and other objects. Tracking foreign satellites, monitoring launches, and supporting intelligence operations play a special role in the national security and international relations systems today. These tasks are a priority for special services and intelligence agencies, as they enable timely access to valuable information about potential threats, new technologies, and strategic plans of other states. Within these efforts, particular importance is given to controlling satellites in orbits outside the country's territory, as well as tracking any anomalous objects or phenomena occurring in outer space. However, it is important to understand that this field involves many nuances and hidden aspects that often remain beyond public knowledge. When someone with sufficient authority and access conducts surveillance of space objects, or automated systems detect unusual signatures or signs, such information typically remains classified. For example, when automated systems detect a comet or another space object perceived as an anomaly, this data often does not reach open sources. The reason lies in the secrecy protocols. Information about such objects is stored in closed information channels accessible only to a narrow circle of specialists and leadership structures. As a result, official releases confirming the detection of such objects do not appear in the public domain, and no data is published for the scientific community or civilian researchers. All of this goes through complex declassification procedures that can take years, and only after their completion can certain information become accessible to the general public. Allow me to clarify one important point, as this is often where various speculations and misinterpretations arise. Rumors about military interceptions, secret images, or observations of space objects allegedly discovered during special operations or using secret technologies are actively spread on the internet. For example, popular videos on YouTube or forums like Reddit feature claims of unusual signatures, reports of emergencies, or even orders for special observation missions targeting specific celestial bodies. However, all these claims are generally not supported by verifiable sources. No official documents have been published, nor have any confirmations or leaks appeared that could substantiate such information. This is an important point. All these stories circulating online are more like narratives and speculations based on assumptions and possible scenarios rather than proven facts. They are built on what might be, not what is confirmed. I mention them precisely because such legends and myths have become part of the popular culture surrounding the topic of secret space observations and space intelligence. But it is essential to understand that none of these stories are confirmed by official information and lack a solid evidentiary basis. They are part of the informational background in which various theories and speculations emerge and spread. So why then are data obtained through specialized sensors not published, even if they suggest the detection of unusual objects? Why are the results of observations not disclosed even when there is evidence of unusual signatures or recorded anomalies? There are several reasons. First, protecting the capabilities of one's own technologies and observation tools is a priority. Revealing what exactly and how satellite or ground-based reconnaissance systems see could provide an adversary with valuable information about the nature and limits of the system's capabilities. This, in turn, would help the opponent understand what they need to hide or how to avoid detection. Second, there is the aspect of the secrecy of the mission itself. Reconnaissance missions, especially those related to space observation, are strictly classified. This is done not only because it is important to determine what was discovered but also where and how the observation took place. Publishing data about observations from 3 or more satellites, for example, could inadvertently reveal their orbital parameters, the sensitivity of telescopes, or the level of automation used in reconnaissance systems. Such information could give an adversary valuable clues about the tactics and capabilities of intelligence agencies. Finally, an important factor is the strategic deployment of new datasets provided by NASA, which consistently maintain a certain sequence and structure similar to previous ones. If 2 leading space agencies simultaneously observe the same celestial object, such as a comet, during overlapping periods, their data should form a logical and consistent picture. In particular, parameters like the comet's brightness, its position in the sky, and spectral characteristics should match within the allowable measurement errors. This means that if both agencies confirm the similarity of these measurements, such agreement will serve as strong evidence of the correctness and reliability of the obtained results, while any significant discrepancies will warrant a more detailed analysis and discussion. Conversely, if the measurements do not match or if data from one source show something radically different, it will be a warning sign requiring immediate attention from the scientific community. Such cross-checks, comparisons, and mutual validation of results are essential to ensure their consistency, honesty, and reliability, and they form a vital part of the scientific methodology. This principle is equally applicable to orbital calculations. The Center of Minor Planets gathers observations from around the world, aggregates them, and publishes updated information on the object's orbital parameters. These parameters are calculated based on all available data, which helps improve the accuracy and reliability of orbital models. When spacecraft orbiting Mars or other planets contribute their observations, this data must be integrated into the overall system, and any changes in orbital characteristics should be reflected in the updates published by the Minor Planet Center. For example, if NASA spacecraft orbiting Mars record significant changes in the position or velocity of the orbit, this information will necessarily be reflected in new versions of the orbital elements. Conversely, if such data are not provided or are absent, the orbital parameters are determined solely based on ground-based observations, which, although useful, are still an incomplete and less precise approach. In such cases, the accuracy and detail of the obtained information are significantly lower. This raises an important question about the possibility of obtaining higher resolution images and data. Some statements suggested that artificial structures might exist in tall buildings on the surface of Mars or in their nearby structures, possibly even evidence of technological activity. However, let's carefully reconsider the capabilities of modern observation methods. Tall buildings on the surface of Mars, considering the typical resolution of orbital cameras, which is about 30 centimeters per pixel, can only be detected when in very close proximity to the surface. At a distance of 30 million kilometers, which is roughly 10 times the distance between Earth and the Moon, the resolution, compared to this, is approximately 1 microradian. Under such conditions, 1 microradian translates to about 30 kilometers per pixel, not 30 centimeters. This means that from such a distance, it is impossible to resolve even the smallest surface details or detect structured objects such as panels, engines, or antennas. We cannot address issues related to surface detailing or internal structures because this requires significantly higher measurement accuracy than what is currently available. Moreover, observations from orbit can only capture general brightness parameters and their variations, which inform us about the shape, activity, and dynamics of the comet or other object, but do not allow for detailed imaging of their internal structures. The idea that one could see individual panels or propulsion systems on a comet or other celestial body based on photographs taken from a great distance is entirely unrealistic. To discern such details, it is necessary to approach the object much closer, reducing the distance several times, and to use high-resolution cameras. This does not mean that tall buildings or artificial structures are impossible to detect at all. Rather, it suggests that expectations should be realistic and aligned with the capabilities of current technology. One should not rely on the assumption that orbital observations alone can reveal everything. Even if all classified assets somehow detected something unusual, and even if this data remains strictly confidential and inaccessible to the public, ultimately, all information about what is happening would need to be integrated into a single, coherent picture. If, as a result of this integration, it turns out that individual fragments do not match or contradict each other, then serious questions and doubts would inevitably arise. As long as observations and data continue to come in and be recorded, we remain in a state of observation, carefully monitoring what is happening, noting possible gaps and shortcomings, and awaiting new discoveries. But let's try to look at the situation from a different perspective, to momentarily detach from our usual assumptions, and consider what could be revealed during this close pass of Mars, or what might change in the object itself. Were there hidden opportunities in this approach that we have not yet guessed, or could it have triggered unexpected effects worth contemplating? Let's explore together what influence the proximity of Mars might have on the environment and on the object itself. This topic deserves special attention, and we will continue to examine it within the framework of the 8th part of our study, the effect of Mars proximity. This section will discuss hidden possibilities and potential adjustments that could arise from such a close approach. When an interstellar object, whether a comet or an asteroid, approaches a planet at a distance of 30 million kilometers, various events can occur, albeit not as dramatic as a collision or capture, since this distance is too great for such events. However, subtle interactions can take place at this range, capable of leading to important scientific discoveries or generating more speculative scenarios that attract strategic interest. Let's start with the basic physical aspects. The planet Mars has its own gravitational field, which, although weak at such a distance, still exists. One can perform calculations of tidal effects and determine possible perturbations in orbital motions caused by this gravitational interaction. Assuming the size and mass of the object are similar to 3 atlases, the influence of Martian gravity at closest approach would be measurable, albeit very slight. Of course, such a small difference can be detected using precise astrometric methods by measuring deviations in the object's position. This would be quite useful because if observations do not reveal a significant mass for Mars, it would help narrow down the possible trajectories of the interstellar body and enable more accurate predictions of its future path. This approach is a kind of natural experiment based on the laws of orbital mechanics, which helps to better understand the behavior of such an object. But Mars's influence is not only gravitational, there is also a surrounding space environment that deserves attention. Mars has a weak magnetic field, remnants of ancient dynamo chaos, and a tenuous atmosphere that extends far above the surface into what is called the exosphere. Additionally, it is constantly exposed to the solar wind, a stream of charged particles emanating from the Sun. When the solar wind interacts with the upper layers of Mars's atmosphere and its weak magnetic field, complex processes occur. Shock waves form, magnetospheric tails are created, and various ionized regions develop. If an interstellar object, for example, 3 atlases, were to pass close to these formations or even through them, which, again, is impossible at a distance of 30 million kilometers, interesting interactions could be observed. For instance, the coma of a comet, saturated with ions and charged particles, could interact with the environment upon entering the magnetosphere or the influence zone of the solar wind, causing deviations in the tail's shape or triggering bursts of excitation. These effects could be visible, and studying them would provide valuable information about the environment around Mars and the properties of the interstellar object itself. Within modern research programs and tools, such as spectral analysis, lines of emission characteristic of various molecules present in the atmospheres or comas of comets and other cosmic objects can be detected. These spectral lines can be very fine and difficult to distinguish, but they offer valuable insights into the composition of the observed bodies. Especially important are the asymmetries that appear in the spectra. They can indicate reactive activity of the comet, meaning that dynamic processes involving gas and dust ejections are occurring inside it. When we observe a comet from a distance of about 30 million kilometers, the resolution of our instruments often does not allow us to see the tiniest details of its structure. Nevertheless, even at such a distance, we can identify general patterns in its behavior, for example, changes in brightness, color shades in various filters, or spectroscopic characteristics. All of this helps us understand how the comet reacts to solar radiation and what processes are occurring within it. However, it is important to remember that under these conditions, we cannot observe the smallest details. For instance, we won't see the engines of a spacecraft if it happens to be nearby, nor can we determine the precise surface structures of the nucleus if it is very small or compact. All we can obtain are general indicators such as brightness and spectral features, which serve as indirect signs of the comet's activity. One of the most informative parameters is the brightness of the object. Depending on the time of observation and the filters used during imaging, we can determine its color shades. This data allows us to draw conclusions about the composition and state of the comet. In some cases, spectroscopy helps identify the presence of certain molecules and elements, as well as their concentrations. If a comet experiences an outburst, a sudden increase in activity, it often manifests as a spike in brightness. Such outbursts occur when a fresh patch of ice appears on the comet's surface and is suddenly exposed to sunlight, or when a rock breaks apart, releasing trapped gas and dust from beneath the surface. Despite their dramatic appearance, these phenomena are natural and common for such celestial bodies. Detecting a spike in activity when the comet is within a Martian observation window is an interesting fact, but it does not necessarily indicate any unusual anomaly. Now, let's move on to an important aspect, the influence of the solar wind. Space weather is constantly changing. The sun continuously emits a stream of charged particles called the solar wind. This stream is not static, its density and speed fluctuate depending on solar activity. Sometimes, large eruptions occur on the Sun, coronal mass ejections or CMEs, which are powerful bursts of plasma and magnetic fields. Such ejections can travel through the entire solar system at high speeds, creating magnetic and electromagnetic disturbances. If a similar ejection reaches the area where a comet is located, especially during a Martian observation window, it can cause a significant increase in its activity. As a result, the particle flux reaching the comet increases, and it temporarily becomes brighter. This effect is not unusual, it is well documented in the behavior of comets within the solar system. After a coronal mass ejection, the brightness of the comet can remain elevated for several hours or even days, depending on the strength of the ejection and the comet's response. If, during observations of the comet within the Martian window using spacecraft such as SOHO or STEREO, a coronal mass ejection was recorded, along with an increase in solar wind intensity, this fully explains the observed brightening without the need to introduce any exotic hypotheses into the equation. Although it cannot be definitively stated that there is always a causal relationship between the ejection and the comet's activity outbursts, in this case, the likelihood that solar activity influenced its behavior is quite high. Unfortunately, to date, there are no concrete data on coronal mass ejections that occurred in early October of the year 2000. Samples of matter from the interstellar object, which are sometimes discussed and subject to hypothetical speculation, are most likely still purely hypothetical thought experiments. In reality, despite numerous assumptions and fantasies, such samples have not been obtained and could not have been obtained for several objective reasons. One of the main reasons is the incorrect geometry of the situation, which would hinder the successful collection or return of such samples. Additionally, the density of particles from which these hypothetical interstellar samples might consist was too low to ensure a high probability of capture or delivery to Earth. In fact, none of the Martian orbiters, even the most modern and equipped with the latest technology, would have the capability to return such hypothetical samples. Therefore, despite all the fantasies and scientific discussions, this scenario remains more of a mental experiment than a real possibility. However, such reflections are more than just a mental game. They are a useful thought experiment that helps us understand what technological capabilities might emerge in the future within new interstellar missions. It demonstrates how advanced our technologies could become and what we can expect if we decide to send more complex and ambitious space expeditions. Regarding the Martian atmosphere and its variability, modern orbiters such as MAVEN are sensitive to the influence of the solar wind and the state of the upper layers of the Martian atmosphere. These instruments are specifically designed to measure plasma properties, magnetic fields, and energy particle fluxes, allowing scientists to obtain important information about the planet's atmospheric dynamics. If significant changes in solar wind conditions had occurred during observations, MAVEN would have definitely recorded these changes. In other words, the instruments on this spacecraft are capable of detecting even the slightest fluctuations in solar activity that could affect the Martian environment. Moreover, if during this period there had been any indirect influence in the vicinity of the planet, such as the presence of a comet releasing ions and forming a coma that extends through interplanetary space, MAVEN might have detected these signs. It is capable of registering changes in electromagnetic fields, plasma density, and energy fluxes, which suggests that even very weak and indirect effects could be observed. Of course, all these assumptions remain quite speculative, and given the vast distances involved, such effects are likely to have very small physical amplitudes and are unlikely to be detected. Nevertheless, the data obtained by MAVEN could provide valuable information about the state of space weather at that time. This information helps scientists understand how variable solar activity is and how it influences the planet's environment, as well as providing context for further research. When scientists later compare MAVEN's measurement results with data on comet activity that might have been present during the same period, it will open up the possibility of making important conclusions. For example, they could determine whether the comet had any influence on the atmosphere and magnetosphere of Mars. If observations show correlations between changes in MAVEN's data and comet activity, this could form the basis for publishing significant scientific papers on large-scale interactions within the solar system. However, it should be emphasized that in most cases, such interactions tend to be either insignificant or entirely absent. Regarding electric currents, their parameters and magnitude often align best with scientists' expectations that no dramatic events occurred on or around Mars during that period. Comets approaching the planet are generally not unusual, as their appearance near Mars is not a rare phenomenon. At the same time, interstellar objects are extremely rare, and their passing close to the planet is an exception. Physics based on modern theories does not predict any dangerous, wild, or unexpected interactions if the distance is around 30 million kilometers, roughly the Earth's distance. We often encounter questions that cause some discomfort and even a certain confusion. Imagine that secrets exist, and these secrets concern the ways in which space and its mysteries are concealed from the entire scientific community of the world. And also, from the general public, which increasingly leans toward a skeptical perception of official explanations and believes that many facts and discoveries are carefully hidden from the eyes of the masses. A natural question arises. How exactly is the mystery maintained? How are knowledge and discoveries related to space and its secrets concealed? How is the mechanism of silence implemented? If the issue concerns concealing important discoveries, such as those related to the mysterious 3 Atlanteans, how is this concealment carried out? Not in Hollywood movies or science fiction scenarios where dark figures use fire alarms to destroy evidence and confiscate hard drives, but in reality, how does it happen in practice? Why do bureaucratic procedures, rather than special operations, become the tool for hiding? Why are lies and denial perceived as a reliable shield protecting the secret? Let's examine in detail the mechanisms that create silence, both legal and more troubling hypotheses, since they are what generate the illusion of impenetrable silence. It's worth starting with the simplest yet most effective methods, rules and procedures that allow the flow of information to be turned off. These exist, and their use is highly effective. For example, when the operation of key structures like NASA is temporarily suspended, all infrastructure related to public communications essentially comes to a halt. Not because someone issued orders not to publish news, but because employees responsible for updating websites or preparing press releases are simply forced to cease their activities. At that moment, they are legally restricted in their actions and therefore cannot publish any new information. Technically, websites are not updated, press releases are not issued, all of this happens not out of whim, but according to established procedures, because communication specialists, journalists, and other experts responsible for communication are compelled to stay silent. Social media channels usually go quiet as well, because accounts and pages are in a state of managed silence. Their owners simply do not have the right to publish new posts or comments. This is not intentional suppression but rather a procedural silence. Nevertheless, its effect is no less powerful. The public hears only silence. And most importantly, this method of silence is predictable and fully legitimate. NASA develops continuity plans that explicitly state that in certain situations, such as shutdowns or suspensions, communications will be halted. So, if you were interested in keeping some important information secret, shutting down communication channels would be an extremely convenient tool for you. You wouldn't need to order anyone to stay silent, you simply let the procedures take their course. They themselves ensure the necessary silence. Now, it is important to distinguish two concepts, embargo and classification. because these terms are often confused, and understanding their differences helps better grasp how exactly information concealment is implemented. An embargo in scientific circles is an agreement where researchers agree not to disclose the results of their experiments or observations until a specified date. Part 40 of 82. This is usually done to synchronize publications or prepare materials for release in scientific journals. Such agreements are temporary, voluntary, and do not compromise any state secrets. They serve merely as good practice to prevent leaks and misinterpretation of data. In contrast, classification is a strictly legal mechanism enshrined in law. Information subject to classification is protected by law, and its disclosure can lead to serious consequences, including criminal prosecution. Classification levels, confidential, secret, and top secret, require special handling, storage, and access control conditions. They are regulated by specific protocols, and violating them is very difficult, as it entails significant risks. Publications of data obtained from the Hubble telescope are regularly delayed and postponed, which has become a familiar occurrence for specialists and interested observers. From time to time, it is noticed that websites where mission results are supposed to be published freeze or operate with delays, causing certain difficulties for those awaiting new data. All of this is documented and happens almost every time during major update or publication cycles. Historically, during periods when scientific programs were closed, for example, in the 18th and 19th years of this century, delays reached about 35 days, often negatively affecting planning and related projects. Scientists publicly complained about declining productivity and postponed publications, which was quite a common phenomenon, since such delays are more the norm than the exception. Regarding potential delays in publishing data from the Atlas, even if they occur, such delays are more likely to conform to the long-standing trend rather than indicate any special or exceptional treatment. In other words, these situations are more of a pattern than evidence of hidden reasons or special conditions. However, the most interesting part begins here, because everything is complicated by the issue of format and barriers surrounding the processing and publication of astronomical data. Most people do not realize that raw astronomical data are not just simple images that can be opened with a regular photo viewer or similar software. In reality, these raw files are presented in specialized formats, such as FITs. This format is not just a container for images but a flexible data transfer system that requires specialized software to read and interpret. The size of these files is often very large. They contain not only pixel brightness and color values but also a wide range of metadata, including instrument settings, calibration information, timestamps, and coordinate data. All of this is necessary for a comprehensive analysis and interpretation of the data, which requires a certain level of expertise. To understand and correctly interpret such files, one must have knowledge of the tool's operation, the process of its calibration, the noise and artifact characteristics, as well as methods for their removal. All of this creates a natural barrier for the general public and non-professional observers. Even if NASA were to publish all raw data tomorrow, most people would not know what to do with it or how to analyze it. Only a narrow community of specialists, astronomers, engineers, and analysts would be able to process and interpret it effectively. This is not a sinister phenomenon but simply a technical feature and a reality of scientific work. However, because of this, even with full data disclosure, the information would not be entirely accessible to the general public. Extracting meaning from it requires knowledge and experience that most people do not possess. In other words, access to information does not equate to understanding it. This is part of a broader picture characteristic of large scientific and research organizations. Such structures often have a phenomenon called compartmentalization, meaning the division of information and responsibility across different areas. This is especially true for organizations working with secret or confidential programs. In such cases, different teams operate at separate stages of the project, often without a complete understanding of its overall progress. There is no single picture, only individual pieces passed along the chain, often intentionally. This division is neither accidental nor malicious but a security measure deliberately implemented to limit potential damage. For example, if someone attempts to compromise the project or reveal its secrets, either accidentally or intentionally, such compartmentalization helps reduce the potential harm. In civilian science, similar division often occurs due to professional specialization. People working, say, on orbital calculations for Mars are no longer the same specialists engaged in spectroscopy or other types of analysis. Each focuses on their own area, and no one has a complete overview. When documents are unavailable and information reaches journalists, it already raises certain doubts and assumptions. In such cases, former employees of relevant organizations sometimes make public statements about what transpired, trying to shed light on what is being concealed. However, it is important to emphasize, their words do not mean that such events did not occur at all. In the current era of digital technology and widespread distrust of official sources, such leaks of information are not uncommon. From time to time, we observe how secret programs, Pentagon documents about unidentified flying objects, intelligence operation details, all of this unintentionally or intentionally leaks into the public domain. Leaks can occur for various reasons, and if there were, so to speak, a smoking gun, for example, concrete evidence of a mysterious mission or project, then someone could have long ago made it public. However, the fact that such evidence has not emerged prompts reflection. Perhaps there were no serious incidents or secret operations at all, or the circle of people with access to the information is so small that the likelihood of leakage is minimal. Another possible reason is that we are still in the early stages of information gathering and disclosure, and the process of leaks takes time to come to light. Time is the best judge in such situations, and only it will reveal the true state of affairs. To help skeptics and those wishing to assess the situation independently, there are several methods and tools of analysis that can be used once the first pieces of information start to appear. The first is integrity verification of files. In the digital world, files related to secret research are often protected by checksums. If someone modifies a file after its creation or signing, this can be easily detected by comparing the current checksum with the original. This approach helps determine whether the file has been tampered with or not. The second important aspect is checking timestamps. Each digital image or document contains information about its creation or last modification time. These timestamps should correspond to the expected timeframes during which, according to official data, certain events took place. For example, if an image purportedly showing a comet is timestamped at a moment when, based on observations, the comet was in a different part of the sky, there are grounds to doubt its authenticity. The third step is analyzing data on the status of the spacecraft or device provided alongside observations. Usually, each record is accompanied by metadata, information about direction, temperature, energy levels, and other parameters characterizing the equipment's condition. Anomalies in this data can serve as indicators of whether a particular observation is standard or contains deviations suggesting possible malfunctions or other unusual circumstances. The fourth method involves cross-checking results with other missions and observers. For example, if the European Space Agency and the National Aeronautics and Space Administration, NASA, simultaneously observe the same object, their results should match or, at least, be very close. Discrepancies in the data, especially if significant, require special explanation and may indicate falsification or error. This approach is not a sign of paranoia, but rather the foundation of the scientific method. Trust but verify. In a global system of observation and research, where numerous independent centers and amateur groups track celestial objects, the presence of discrepancies is a signal to be cautious. For example, if observations by amateurs involved in the Minor Planet Center show a different trajectory or parameters than official data, it should raise interest. After all, organizations like the Milky Way or the Minor Planet Center publish their residual data, and anyone can check how accurately the model matches the observations. Moreover, coordinating efforts between different countries, agencies, and independent observers to conduct large-scale and precise verifications is practically impossible if a widespread conspiracy or information concealment existed, because then, we want the concept of disconnection to mean more than just a certain aspect of budget policy or financial planning. We aim for it to acquire a deeper meaning, to become a symbol of something unusual and exciting, since the familiar and mundane often evoke only boredom. We are not immune to this inner desire to see something extraordinary in what is happening, something that goes beyond standard explanations. None of us is free from this urge. It is natural and inherent to everyone. At the same time, desire alone cannot create truth. It merely pushes us to seek evidence, confirmations, or refutations. And right now, we are faced with concrete evidence, or the lack thereof, of active suppression of 3 key data points related to Atlas. However, these pieces of evidence are either very scarce or entirely absent. What do we have at our disposal? Primarily, procedural silence, technical barriers, and organizational difficulties. All of this is quite real and understandable, yet at the same time, mundane and unremarkable. The question is, are these standard explanations sufficient to consider them final, or is there something more hidden behind these simple words? Something lurking in the darkest corners, in the depths of the unknown? To answer this question, it is necessary to formulate competing hypotheses and analyze them carefully. That is exactly our approach, to present 6 hypotheses that could explain what did or did not happen during the so-called Martian window in early October 2025. For each, I will outline its main idea, provide supporting evidence, and indicate what could serve as falsification, what might disprove or cast doubt on its validity. After all, a hypothesis that cannot be refuted is not science, but merely a story invented for entertainment or speculation. So, let's begin. The first hypothesis is a bureaucratic coincidence. According to it, the shutdown is related to routine administrative procedures that accompany the work of space agencies. The explanation is as follows. A chain of random circumstances arose, linking communication gaps and technical failures. NASA assets associated with the Mars program were not observing the comet, or perhaps they were observing it, but the data was still in the queue for processing after the system was turned off. Accordingly, their management was carried out as announced, within standard procedures. The comet was treated as a regular celestial body, and everything was expected to fall into place once the data was finally published. This is the simplest and most mundane explanation, requiring no special conspiracies or extraordinary physical hypotheses. It fully aligns with how government or scientific institutions typically pause operations and how scientific activity develops under such conditions. Supporting evidence for this hypothesis includes NASA's official statements about plans in case of prolonged outages, continuity protocols that clearly specify pauses in public communications during financial difficulties. Plans of the European Space Agency are also openly discussed, with no verified leaks or informant statements indicating a different scenario. The question is, can this hypothesis be disproved? If the European Space Agency publishes data showing that the orbital parameters and analyses of the comet significantly contradict earlier predictions, it would be a warning sign. If NASA releases data indicating that the comet's location or condition does not match ESA observations for the same period, it would raise serious questions. And if independent amateur observers tracking the comet report unusual changes in brightness or position not reflected in official data, it would be another reason for suspicion. The key test is the consistency of all observations. The emission lines of nickel detected in the comet turned out to be significantly more intense and prominent than those typical for ordinary comets. This suggests that the nucleus of this comet is likely enriched with metals compared to more typical icy and rocky bodies we are accustomed to seeing in our solar system. Although this hypothesis is mainly speculative, it is not excluded and does not contradict the possibilities of scientific analysis. In fact, there are asteroids rich in metals, and such objects are found within our system. Moreover, fragments of destroyed or disrupted differentiated bodies orbiting other stars could have ended up in interstellar space, making the hypothesis of an extraterrestrial origin for some of these objects quite plausible. Supporting evidence for such theories most often originates from early scientific reports and discussions in various blogs and scientific communities. A particularly active topic of debate is the fact that some sources, such as blogs and specialized publications, have raised questions regarding unusual size ratios and characteristics associated with the detected nickel lines. However, it is important to emphasize that many of these conclusions are preliminary and often based on incomplete data or interpretations that may be overly aggressive and not fully confirmed. How can such hypotheses be refuted or confirmed? First and foremost, more rigorous measurements and analyses are necessary. For example, constraints on the nucleus size and albedo help estimate the object's mass. If these estimates fall within the range typical for ordinary comets, then the hypothesis of a metallic core loses its strength. Spectroscopic studies allow determination of the comet's composition. If spectra are dominated by water, carbon oxides, as well as typical silicate dust with high metal content, similar to what is observed in comets of our solar system, then the hypothesis of a metallic core becomes unlikely. Additionally, the comet's motion parameters, especially non-gravitational accelerations, serve as important indicators. If the acceleration is related to the outgassing of volatile gases rather than a large mass, the body's behavior will correspond to that of ordinary comets. For example, if brightness curves show rapid decreases or increases, characteristic of fluffy, irregular, low-density bodies, this indicates that the comet is more likely composed of loose ice and dust rather than a solid metallic core. After passing perihelion, if activity and brightness continue to remain at levels typical for standard comets, the hypothesis of a metallic core becomes less plausible and unlikely. The discussion of a hypothesis involving some technological or artificial origin of the object, such as a probe or artificial artifact, is another possibility sometimes proposed by scientists and enthusiasts. In this scenario, it is assumed that the object could be part of another civilization's technology or some artificially created device. Such a scenario exhibits signs different from natural ones, for example, non-gravitational maneuvers that cannot be explained by gas emission or the body's mass. Additionally, such objects may display unusual light curves related to their structure and geometry rather than natural rotation. Spectral signatures that do not match known materials of comets or asteroids, as well as radio signals that appear coherent and narrowband, could all indicate artificial origin. However, it is important to emphasize that to date, no convincing evidence supporting such a hypothesis has been found. In reality, there are neither peer-reviewed scientific articles confirming the artificial origin of this object nor verified signals or orbital anomalies that would require an extraordinary explanation. The main assumptions about a possible artificial nature tend to arise more from human curiosity and the questions it raises. Why did this particular object attract our attention? Why do its characteristics seem unusual? In this case, many scientists agree that the interest in the object and the radio search efforts, which actually only produce noise or natural signals, present a complex challenge. When each conducted test and observation confirms the expected trajectory of the comet, the hypothesis of an artifact or artificial origin of this object gradually loses its plausibility. In such a situation, it becomes clear that the burden of proof lies with those who propose the hypothesis of an unnatural nature of the object, and they must present convincing evidence to disprove the natural explanation. At the same time, the criteria for falsification are clear and unambiguous. Natural explanations must be thoroughly tested and refuted before considering the possibility of an artificial origin. In other words, all hypotheses regarding the natural origin of the comet must be examined with care and rigor to exclude even the slightest chance of an unnatural factor. One alternative hypothesis is the involvement of third parties. It is quite possible that some participant, most likely a state actor with advanced technological capabilities, conducted secret operations near the comet. This could have involved intercepting the object, an encounter, or even an inspection, perhaps during a Martian window, a period when Mars is optimally positioned for interplanetary missions. It might involve sample collection for reconnaissance purposes or even an attempt to alter the comet's trajectory to conceal its true nature or origin. All of this sounds like deep speculation bordering on science fiction, given current technology, but such hypotheses need to be considered to understand possible scenarios. Evidence supporting this hypothesis could include the detection of unexpected maneuvers in the comet's orbit that clearly do not align with models of gas emissions or natural processes. This also includes reports from amateur observers who documented anomalous phenomena, leaks of messages or documents, and testimonies from insiders within space agencies. However, to date, there is no publicly available confirmation supporting these hypotheses. Orbital solutions and observations do not show any sudden unexplained changes in the object's motion, no information leaks have been recorded, and amateur observations remain within the bounds of natural phenomena. In light of this, the question arises: how could such a hypothesis be refuted? To do so, one would need to demonstrate that orbital maneuvers remain unchanged over an extended period and that all observed position and velocity parameters of the comet can be fully explained by the influence of solar gravity and other known physical forces, without the need to invoke interference hypotheses. An important argument is also the absence of Doppler signal anomalies or eyewitness reports that withstand critical scrutiny. If any anomalies had been observed, they would have to be independently recorded and confirmed by multiple sources. If major space agencies such as NASA and ESA, as well as independent observers, published data showing a consistent and continuous description of the comet's trajectory matching predictions and models, the interference hypothesis would lose all plausibility. An essential aspect is also the technological side. Is there currently any country capable of intercepting an object moving at tens of kilometers per second at a distance of 30 million kilometers from Earth within a week's window? The answer is most likely no. Modern technology does not yet allow for such interception, and the hypothesis of needing to conceal such operations implies the existence of secret space capabilities far exceeding publicly known levels. This is an extremely complex task requiring powerful, clandestine systems and programs about which the public and scientific community have no knowledge. Another hypothesis involves secret funding and data collection within the so-called black budget. Military or intelligence agencies could have observed such phenomena. None of this data has been officially published before, and the question of how to falsify it remains relevant. Currently, it is impossible to directly prove or disprove their authenticity. However, there is an opportunity to analyze the sequence of events that could indicate the truthfulness of one hypothesis or another. If civilian information about events related to the comet were fully disclosed, and enough observers capable of comprehensive and consistent verification appeared, the need to keep secret data would be significantly reduced. In case of gaps in information, unclear discrepancies, or strange details in public opinion, it becomes evident that the existence of secret data can only serve as a temporary measure supporting the hypothesis of the persistence of a particular version of events. The practical test lies in whether, over time, scientific records and observations can acquire a meaning consistent with the justified conditions and logic on which they are based. If this occurs, the presence of secret data becomes unnecessary to explain the phenomena. Otherwise, open questions remain that require further investigation. Moving on to the sixth hypothesis, the hypothesis of planetary interaction. According to it, the close passage of Mars could have triggered or coincided with temporal anomalies in comet behavior caused by cosmic influences on the environment. It is possible that a weak impact from solar wind, a coronal mass ejection, or interactions with Mars's magnetosphere induce temporary changes in the comet's characteristics. For example, observed brightening, asymmetry of the coma, or spectral shifts. Such phenomena would be of scientific interest because they confirm the possibility of cosmic interactions without implying anything supernatural or unusual. Supporting evidence could be obtained from modern space weather data, which record intensifications of coronal ejections, solar wind activity, or other manifestations of solar activity during relevant time windows. For instance, data from the MAVEN mission showing disturbances in the space environment around Mars, as well as observations of brightness spikes or increased activity of the comet during the suspected events. All of this constitutes verifiable and falsifiable information. If the dataset regarding Mars does not show significant changes in brightness or spectral features, the hypothesis of a link between space weather and comet behavior loses its strength. If, on the other hand, changes are observed but space weather data show no unusual phenomena, the hypothesis would need to be revised, with conditions or mechanisms clarified. However, if both the comet and the space environment demonstrate coordinated changes, for example, brightness surges and activity coinciding with potentially influential factors, This would be strong evidence supporting the hypothesis. Such a scenario would represent an important contribution to scientific understanding of the interaction between cometary plasma and the surrounding environment, and these observations could serve as valuable confirmation of the hypothesis. In this case, we would have an example of a scientific approach based on observation, which is understandable and conducive to expanding our knowledge of interactions among cosmic objects. For each hypothesis, I consider the expected predictions and the types of data that could confirm or refute the proposed assumptions. Let us consider who and how could carry out these verifications. For testing the first, second, and sixth hypotheses, there are space probes and scientific teams capable of providing direct evidence. For example, the mission Mars Express of the European Space Agency and the team from the ExoMars program will provide images and spectroscopic data that can offer a clear understanding of the surface and atmospheric conditions on Mars, as well as possible interactions that confirm or refute hypotheses. Specialists working with data from the Small Planet Center and the Orbital Dynamics Department will monitor changes in orbital parameters and update them as new information becomes available, thereby testing hypotheses related to orbital dynamics and planetary interactions. Ground-based observatories, such as those after the end of the Joint Earth Observation Period, which begins in late November and continues throughout December, face a crucial moment for astronomers and space enthusiasts. It is during this time that ground telescopes equipped with the most advanced instruments will be able to detect the appearance of the mysterious comet again after it disappears from the sun's glare. These observations will be key, as they will provide independent and objective information to verify all previously made statements or assumptions formulated during the so-called Martian window. This is a special period when conditions for observing objects near the red planet are most favorable. The data obtained in December will serve as a criterion for assessing the accuracy of predictions based on information gathered during this window. If the brightness of the comet, its activity level, and the trajectory calculated in advance are confirmed, it will serve as strong evidence supporting a specific hypothesis, known in the scientific community as the first hypothesis. Conversely, if unexpected deviations, discrepancies, or anomalies occur, the remaining hypotheses will remain relevant and require further investigation. I would like to emphasize the importance of choosing the first hypothesis in this situation. It is called the bureaucratic coincidence, and is considered the most economical in terms of assumptions and explanations. It is based on the minimal number of assumptions and the maximum consistency with already known facts and observations. This does not mean that it is automatically regarded as the truth, but it is the basis on which analysis is initiated. In scientific practice, there is a principle known as Occam's razor, which states that unnecessary multiplication of entities or hypotheses that complicate explanations should be avoided. In other words, if a simple explanation exists, it should be accepted first, and more complex and exotic theories should only be considered if no alternatives are available. One should not assume conspiracy unless this explanation is supported by facts, nor should one believe that extraterrestrial technologies interfere with processes until convincing evidence is found. However, it is important to remember that paranomy is not the same as certainty. Following the evidence must be done regardless of where it leads, even if it means acknowledging the need for more complex and unusual explanations in the future. A historical example that supports this approach is the case of Oumuamwa's discovery. Initially, astronomers considered the hypothesis of a possible artifact in space, but ultimately, after thorough research and data analysis, a natural origin for this object was accepted. This is an example of how scientific rigor and consistency can lead to the correct truth, without succumbing to excessive hypotheses and assumptions. Similarly, in our situation, all possible explanations are critically examined and tested against the facts. Therefore, our task is to determine which hypotheses are most likely based on the available data and observations. There are 6 of them, arranged roughly by plausibility. The first hypothesis is at the top of this list. It is the most probable and well-founded. The second and sixth hypotheses are scientific alternatives with a certain degree of plausibility and deserve attention. The fifth hypothesis is a falsifiable, but still plausible assumption based on how secret systems and previously unseen mechanisms operate. The third and fourth hypotheses are more distant scenarios that require additional evidence, which currently does not exist. All 6 hypotheses, however, are subject to testing, at least indirectly, through incoming data and observations. It is this situation that makes the current story so exciting. We are not forever stuck in a cycle of guesses and assumptions. As is known, space does not hide its secrets well, and the light reaching us preserves its traces, movement trajectories and streams of information measured. In December, we will witness the results and consequences of everything that happened in October, as it is during this month that the events related to space objects, which were in a dead zone, will fully manifest. These phenomena, like a complex recipe composed of many ingredients, demonstrate how objects in space respond to the conditions they find themselves in. Who is ready to observe this unique spectacle among the stars? Of course, ground-based telescopes, the main tools designed for such observations. The largest and most modern observatories, located in both hemispheres of our planet, will focus on studying comets that currently have sufficient brightness to become objects of close scientific attention. If these comets remain visible to the naked eye, including them in the list of priority observation targets becomes almost mandatory. The brightness of these celestial bodies, that is, their visible luminosity, directly depends on their level of activity and the remnants left after their formation and perihelion passage, the closest point of their orbit to the Sun. After perihelion, over the course of several days or weeks, some comets gradually begin to brighten, reaching their maximum brightness, and then quickly fade as they move away from the Sun and, consequently, lose their activity. Other comets can remain active for a longer period, sometimes for several weeks or even months, demonstrating stable behavior and continuing to shine. However, to accurately determine whether a particular comet exhibits active or rapidly fading behavior, additional observations are necessary. This can only be established after thorough study during monitoring. For this purpose, the most advanced space telescopes, Hubble and the James Webb Space Telescope, are used. These powerful instruments can provide unique data, provided their schedules permit. Time on these observatories is a valuable resource allocated according to strict schedules. Observation proposals are submitted several months in advance of the planned date, and obtaining permission to use these facilities is a competitive process that requires prior preparation and justification of the scientific importance of the research. Nevertheless, there is a possibility of allocating time for unexpected and urgent events, such as the sudden discovery of an interstellar comet or a meteoritic object arriving from deep interstellar space. In such cases, scientists can request urgent observations, and time will be allocated for them. The James Webb Space Telescope plays a particularly important role in such observations, especially its infrared capabilities. Thanks to this part of the spectrum, scientists will be able to study the heat emitted from the comet's nucleus in greater detail, as well as determine the composition of dust particles and gases surrounding the object. This will provide valuable information about the physical characteristics of the comet and help understand what substances it consists of, as well as how these substances interact with each other and with sunlight. Additionally, there is a mission by the European Space Agency, Jupiter Icy Moons Explorer, or simply JUICE, which is designed to study Jupiter and its moons. According to planning documents, this spacecraft has a potential window for observing a comet or interstellar object in November 2025. Currently, the spacecraft is near the inner part of the solar system, moving toward a gravity assist, so-called gravitational maneuver, that will ultimately direct it toward Jupiter. During this cruise, the spacecraft's instruments, under favorable geometric conditions, will be used to conduct observations. The thermal regulation constraints and technical parameters do not allow for cameras and spectrometers to be turned on at any moment. However, if the positioning of objects and the brightness of the comet are suitable, JUICE will be able to provide unique data by observing the object from a different angle than the Earth's. This will be especially valuable for measuring parallax, a slight shift relative to the background, which will help determine the distance to the object more accurately, as well as for cross-checking data obtained from different vantage points. The priorities for these observations are clear and driven by the most important tasks. First, let's now focus in more detail on an important topic related to the preservation and protection of data. I mean a comprehensive set of efforts involving archiving observations and verifying their authenticity, as well as creating a system for cross-checking the received information. This process becomes particularly relevant when official organizations begin publishing their data, whether at the conclusion of NASA or European Space Agency missions, especially when they release information on regular, familiar timescales. Instantly, without delays, the community must respond and act in a way that ensures this information is recorded and preserved. To do this, it is necessary to upload raw files, store them in archives with precise timestamps, and create additional backups to protect against potential data loss. Why is this so important? Because at any moment, original data can disappear, websites may go offline, files can be moved or deleted. If we want to guarantee that observations remain accessible for future research and verification, we cannot rely solely on official servers or sources. Experience shows that amateur astronomers, citizen scientists, and enthusiasts have been doing exactly this for many years. They use platforms such as archives.org, as well as distributed file systems and community-created databases, which collectively ensure the reliability and resilience of data storage. This approach becomes especially crucial in the context of a project related to the Third Astronomical Atlas, which attracts increased interest from both the scientific and amateur communities, and also faces difficulties related to the closure of certain information sources or access restrictions. In such cases, I strongly recommend that everyone with the opportunity and technical means actively document and preserve official releases and publications. This will help create a comprehensive and reliable database that can be referenced in the future. One of the most valuable tools for this purpose is electronic spreadsheets. They can be used to compile all published information about observations: date, exact time, observer's name, instrument used, geographic location, measured value, and any additional notes. By creating such a table or database, one can begin to look for patterns and track trends within it. For example, compare whether the brightness measurements from different observers match at the same moment, considering the geometric conditions, or identify deviations that may indicate errors or potentially real anomalies. It is important to pay attention to any outliers, observations that significantly differ from the overall trend. These could point to technical inaccuracies or genuinely important, unusual events that warrant further investigation. To do this, it is necessary to contact the observers to understand the cause of such deviations. This control tool helps calibrate and better understand the conditions under which observations are made, as well as identify possible sources of errors or data distortions. This process requires patience and attention to detail. However, it is precisely this approach that helps build trust in the collected information and enhances its scientific value. At the same time, it is important to manage expectations clearly and honestly. Scientific publications and data reports often lag behind actual observations by weeks or even months. Before publishing results, this data must be carefully calibrated, analyzed, and documented. The review, verification, and formatting process takes considerable time, and during periods when observations are paused or limited, delays can become even more significant. For example, NASA might publish a complete dataset several months after the data collection has ended. While this can be frustrating, it should not be taken as evidence of misconduct or hidden facts. It is important to monitor the consistency of dates as well as the quality of the published data. If NASA eventually releases information about Mars, even if these materials seem boring or mundane at first glance, their quality and completeness will still matter. If gaps, unexplained artifacts, or low-quality data are found at critical dates that raise doubts, this should raise concern. In astronomy and space research, many factors and nuances require careful and detailed analysis. For instance, the brightness of a comet as it approaches perihelion, that is, the point in its orbit closest to the Sun, changes under the influence of various natural processes. During this time, processes of ice sublimation and dust ejection activate on the comet's surface, creating a characteristic dust and gas coma around the nucleus. These outbursts not only affect the visual brightness of the object but are also accompanied by gas emissions corresponding to the ices from which the comet is composed. As a result, astronomers observe changes in the comet's light curve, reflecting the dynamics of its activity and rotation. The curve of this brightness, often irregular, indicates the complex and variable nature of a comet's rotation, which may be caused by factors such as uneven mass distribution or an asymmetric core structure. Orbital fitting is an essential tool for determining the precise parameters of such objects' motion, particularly important because it allows for the consideration of small, often non-gravitational, forces acting on the comet. These forces can include radiation pressure, solar wind pressure, or even minor gravitational perturbations from planets or other bodies, complicating the accurate modeling of its trajectory. At the same time, to understand how exactly the comet moves and how its parameters change, scientists use baseline comparisons that help identify any deviations or variations over time. Over years of research, we have studied dozens of comets passing near Earth and confirmed that most behave quite predictably within the framework of known models. However, some features remain that require special attention and analysis. That is why I want to emphasize the importance of monitoring the centers of small planets and their electronic bulletins, such as MPEX, official notifications regularly published to inform about new observations, updates to orbital data, and recent discoveries. These messages are published irregularly, only when there is a need to communicate important information about the current state of objects or new research results. For more precise tracking of a specific object, such as the comet designated C 2025N1, it is necessary to constantly search for and follow updates to its orbital elements. After new orbital elements are published, it is important to compare them with previous versions to determine if significant changes have occurred. For example, has the eccentricity, meaning the degree of orbit elongation, changed, or have new non-gravitational parameters appeared, indicating external forces' influence? These changes tell their own story of the comet's movement and activity, revealing nuances of its behavior and internal structure. Simultaneously, there are public data archives from spacecraft such as Mars Express and TGO, as well as from scientific missions related to the study of planets and their satellites. These archives contain image release logs and metadata associated with observations made during specific periods. When observational results for October are published, these archives can provide precise timestamps and detailed information about who conducted the observations and when. This allows verification that observations were indeed carried out during the declared time windows and confirms the accuracy of the obtained data. Regarding composition analysis, such as spectroscopic data, spectra obtained during observations, I promise that as soon as we have new spectra from the post-perihelion period, we will carefully study them. In particular, we will pay attention to the presence of elements such as nickel and other metals in the spectra. An elevated nickel content in the spectra is a very important and convincing indicator, suggesting the presence of metallic components in the object or processes occurring within it. If several independent spectrographs operating at different observatories or on spacecraft report similar results, this becomes strong evidence. When only one source reports such elevated levels while others remain silent, it is more likely to indicate calibration issues or false positives. In science, observation is highly valued. By observing the celestial sphere in December and then carefully monitoring publications and astronomical reports in the following months, we can notice how an astonishing story gradually unfolds before us. This story is not just about discovering new facts, but about how this information replaces long-standing speculation, turning guesses into verified knowledge. However, there is a possibility that the true secrets of the cosmos are not hidden in the fresh data we receive today, but rather in the old observations we already possess, which for some reason have remained unnoticed or misinterpreted. Perhaps the keys to the mystery are stored in archives, and the answers to many questions are hidden there. Let us discuss the legacy of past missions and the clues that may help shed light on the unknown. A special place in this puzzle is occupied by so-called old missions, which, surprisingly, may contain hidden hints and important clues. Here is a thought that should concern everyone interested in a good detective story among astronomical data. What if evidence of a comet or asteroid under the provisional name, TriAi Atlas, already exists but has been overlooked, buried in archives to which we have had access all along? Isn't it amazing that space missions collect vast amounts of data? These datasets, consisting of images and measurements, are recorded and stored for years, sometimes decades. And only after many years, sometimes at the most unexpected moment, someone revisits these archives in search of specific facts. Suddenly, among numerous images, appears that very detail previously unnoticed, an object visible only upon close inspection. This phenomenon is called a serendipitous or preliminary discovery. It is how our observational lines expand when it comes to comets, asteroids, and other celestial objects. The focus is on data related to discoveries made, for example, on July 1, 2025. But this does not mean that earlier observations are absent or inaccessible. On the contrary, preliminary records are images or measurements taken before the official registration of the discovery. They are usually detected during sky surveys conducted to search for other objects or simply as part of technical equipment checks. If TriAi Atlas had appeared in archives several months or even a year before the official announcement, it could have significantly expanded the database. As a result, the obtained orbital line would become more accurate, constraining possible trajectories and helping to calculate the object's movement with greater precision. The task of any researcher is to find these earlier evidence. To do this, it is necessary to determine which part of the sky the comet was in at that time and perform reverse work, tracing where it could have been earlier. This requires searching for suitable archival images taken by observatories or telescopes during that period. Although such a process often seems tedious and boring, it is quite feasible. Amateur and professional astronomers regularly contribute to these searches. They review archives, compare images, and look for faint signs of the object in old data, which often requires patience and carefulness. Another approach for retrospective searches is datasets obtained by spacecraft operating in orbit around Mars. These spacecraft take thousands of images, most of which are intended for studying the planet's surface. However, among these images are frames taken specifically for instrument calibration or wide-angle sky photographs used to check equipment functionality. If by chance, a frame captured the sky at the moment when TriAi Atlas was in the field of view, even faintly or in the background, such data could become valuable. Of course, the chances that the object was captured on such a shot are very small. In this case, a comet or asteroid would be very tiny and dim. But still, the probability is not zero. Crowdsourcing could help here, mass collective effort. 3 objects, which can conditionally be called the 3 atlases, have come into focus. These bodies are located roughly midway between classical comets and more unusual celestial objects. They possess a coma resembling a comet-like structure and demonstrate activity that could well be characteristic of a comet. However, their mass and composition raise many questions. The uncertainty in these characteristics causes doubt and prompts further investigation. Using known objects such as Oumuamua and Boris as references, we can attempt to predict which categories these bodies might belong to. If the 3 atlases turn out to be more similar to Boris, then the entire story takes on an interesting but quite natural character. At the same time, if their properties resemble those of Oumuamua, which has unexplained features, questions about the nature of these bodies will only increase and will require additional explanations. To begin with, one could consult archives of space and ground-based observations to find possible preliminary images or data taken before July 2025. The volume of available archives is very large. Images captured by telescopes like Hubble, as well as ground surveys such as Pan-STARRS, Catalina Sky Survey, or Zwicky Transient Facility, allow for the examination of large sky areas over extended periods. These archives cover years and can help identify earlier images of the suspected objects. Regular searches for predicted comet positions in the archives could lead to the recovery of data on its early appearances, significantly expanding the orbital parameters and improving the accuracy of the trajectory determination. Each such new observation increases the length of the orbital arc, making the motion model more precise and reliable. The Center for Small Bodies actively engaged in such issues encourages these initiatives. It gathers preliminary information about discoveries, which are subsequently confirmed and supplemented with new observations. Regarding the 3 atlases specifically, there are already several preliminary observations made since the end of June this year, 2025, but earlier cases may also exist, which still need to be found and confirmed. Now, an unexpected turn in our hypothesis. Let's consider NASA missions such as IBEX and Voyager. The IBEX mission, launched in 2008, studies the boundary of the heliosphere, detecting energetic neutral atoms emanating from its edge. Meanwhile, the Voyagers, the first and second interstellar probes to leave the solar system, measure plasma, magnetic fields, and cosmic rays beyond its boundaries. Is it possible to suggest that these spacecraft have recorded something related to the 3 atlases? Most likely, no, quite frankly, not directly. These devices are not intended for tracking objects within the inner solar system, especially such as comets or asteroids. However, if the 3 spacecraft experienced an unusually strong interaction with the solar wind or triggered an unexpected particle flux, then the sensors on these interstellar stations could have detected indirect signs or secondary effects. All of this is to ensure the accuracy and reliability of astronomical data, it is necessary that the measurements obtained during observations are independent of professional observatories and also have a redundancy margin. This means that any information regarding the characteristics of a celestial object should be confirmed by multiple sources to exclude random errors or accidental distortion of the data. If you wish to verify that professional data has not been provided selectively or limited, it is reasonable to compare it with amateur observations. These amateur data should demonstrate consistency with official data. Ideally, the results should match within acceptable uncertainty limits. If amateur observers focus on variations or positions that do not align with official orbital calculations, such discrepancies require deeper understanding and explanation. The amateur astronomy community is not just a group of casual enthusiasts but motivated and attentive observers capable of noticing nuances and details often overlooked by professional instruments. In case of anomalies or unusual phenomena appearing in observational data, it is quite likely that some amateurs would have noticed them and mentioned this on forums, mailing lists, or specialized communities. This makes the amateur community an important source of information, especially for cross-checking professional research results. One way to confirm or refute suspicions is to attempt to align amateur photometry with results obtained, for example, using the Hubble Space Telescope. This telescope, known for its high precision, measured the brightness of the comet and the characteristics of its coma in July, providing benchmark values. At the same time, amateur observers recorded the brightness of the object, conducting measurements with their own instruments. Afterwards, it is necessary to compare the obtained values. Do they match within the established uncertainty bounds? Such an approach is an important step in verifying data, as it helps identify possible discrepancies and understand their causes. It is also important to consider differences in the filters used, observing conditions, and calibration methods. If amateur and professional data do not coincide, the question arises: why does this happen? Perhaps the reason lies in differences in data processing approaches or in the characteristics of the instruments. Investigating such discrepancies is not merely a way to detect errors but also an opportunity to identify real physical changes occurring with the object. For example, a comet might have been brighter during the Hubble observations because a recent outburst increased its luminosity. Studying these situations is interesting because they help us understand the dynamics and behavior of celestial bodies. For a more in-depth analysis, it is important to provide the community with a map of search areas covering different time ranges. The question is, during which periods should we look for possible traces of the comet? The answer lies in the months or even years prior to its official discovery. It is necessary to determine what tools and methods were used at that time, whether ground-based telescopes, satellite instruments, or comprehensive cameras designed for observing meteors and other celestial objects. Understanding which parts of the sky were examined and how to predict the comet's past positions based on its current orbital parameters is crucial. This is achieved through calculations and modeling, providing coordinates and search radii. As a result, we can identify exactly where to look for traces of the object and how to present the findings. A systematic process is carried out at small planet centers for processing and reporting observations. People follow an established procedure, from registering observations to verifying them and officially archiving the data. It is also important to explain the value of negative results, that is, cases where the target object was not detected. If thorough observation and search efforts fail to find the comet where expected, this information is also valuable. It allows setting upper brightness limits, thereby constraining its possible activity level at that time. Such negative results help model the behavior of the celestial object and contribute to a more complete scientific picture. Although less exciting than discoveries, they significantly enhance the reliability of scientific conclusions. If everything proceeds as planned and alignment occurs without complications, the overall situation is considered successful. However, if discrepancies or deviations from expected results are found, it is essential to document these differences and ask clarifying questions to obtain a clear explanation of what is happening. This approach demonstrates responsibility and professional discipline. It is based on principles of careful and attentive analysis, not on paranoia or excessive suspicion. That is how scientific methodology should function, with a constant desire to understand and explain what is happening, without losing sight of details and nuances. This forms the foundation of scientific inquiry. The promise in this case is that outdated data and the efforts of the research community can significantly fill gaps that, for some reason, remain unaddressed in official sources and channels of information. You should not wait for large organizations such as NASA or ESA to inform you about what is happening. You have the opportunity to study available data on your own, make your own observations, and participate in their analysis. Modern tools make this possible. Archives with information are practically publicly accessible and freely available. In most cases, all the research-relevant information is open, and if you have the desire and willingness to learn, you can become part of this process. But it is important to remember that you should not just satisfy curiosity or seek answers to personal questions, but engage in genuine science, follow the scientific approach and methodologies. Before we fully move on to the cycle of observations and analysis, it is necessary to address the most controversial and complex hypotheses, including those that may seem the most fantastical. For example, what should we do if there is a possibility that we have missed signals actually sent by extraterrestrial civilizations? In such a case, it is important to discuss the theoretical hypothesis about the existence of signals and communication from extraterrestrial intelligent beings. The second part of our discussion is dedicated to the question of signals, communication, and the contact hypothesis. Allow me to clearly and precisely express what we mean by this. Specifically, we are talking about incoming signals, which remain largely a highly speculative area for scientific research. The idea that the three atlases are not just random objects but could be carriers of artificial signals or serve as relays has not been confirmed by verified evidence to date. There are no reliable indications or convincing peer-reviewed studies supporting such a hypothesis, nor have there been official statements from leading organizations involved in the search for extraterrestrial civilizations. Despite this, speculation on this topic continues to circulate in various online communities and forums, fueling interest and prompting discussions about the possibility of contact. Therefore, it is important to approach this subject seriously and objectively, to understand what exactly the search for signals entails and what will be needed to convince skeptics of the seriousness of such research. What does a plausible artificial signal look like? Let's start with the main characteristics. Such a signal is most likely to be electromagnetic, since electromagnetic waves, radio and optical, are the most successful in propagating through space. It will typically be narrowband, focused on a specific frequency rather than spread across a broad spectrum, because artificial sources aim to maximize transmission efficiency by concentrating on a narrow and well-defined part of the spectrum. Unlike natural sources such as stars, pulsars, and quasars, which emit signals across the entire spectrum, artificial transmitters are typically designed to concentrate their power on one or several narrow frequency ranges, making them easier to detect. Such signals will also inevitably exhibit the Doppler shift effect, frequency displacement depending on the movement of the source relative to the receiver. If three objects are moving toward or away from Earth, their beam velocity changes, and any transmitted signal will show a corresponding frequency shift. If this shift matches the expected motion of the object, for example, the Doppler effect complicates the search for extraterrestrial signals, as it introduces additional nuances in interpreting incoming data. Specifically, the frequency of a signal emitted by a moving object will shift toward higher or lower frequencies depending on its direction of movement relative to Earth. In the case of a comet moving through the inner solar system, its velocity relative to a planet constantly changes, and along with it, the frequency of the transmitted signal. This means that when observing such an object, the signal frequency will not remain stable. It will shift by hundreds or even thousands of hertz per second, depending on specific conditions and the moment of observation. Therefore, to accurately identify and analyze such a signal, specialized software capable of tracking these dynamic frequency changes over time is required. This approach has become standard in the work of the SETI project, Search for Extraterrestrial Intelligence. However, despite its effectiveness, it is quite resource-intensive in terms of computational power, as it requires continuous and complex real-time calculations. Another significant challenge in radio observations is radio frequency interference, RFI, artificial signals generated by Earth-based sources, which makes the task of detecting extraterrestrial signals even more difficult. Earth is indeed a very noisy planet, as almost all our communication systems, satellites, radars, and numerous electronic devices constantly produce signals that can mimic extraterrestrial sources. As a result, distinguishing genuine extraterrestrial signals from terrestrial noise is very challenging and requires careful analysis. One of the criteria to determine that a signal is likely a terrestrial interference is its independence from the direction in which we point the antenna. If, when aiming at different parts of the sky, the signal appears and disappears at random moments, it is most likely RFI. And if a signal appears at certain moments and its characteristics change depending on the direction in which we point the antenna, or if it repeats at successive positions, indicating a possible connection with movement or specific features of an object, such a signal becomes a subject of special attention. Conversely, if the signal appears regardless of the direction in which we search for it, or if its characteristics do not change when the direction is altered, it is most likely related to terrestrial interference. The topic of public speculation and theories concerning the possible engineering origin of certain cosmic objects was also discussed. In particular, media reports have circulated about alleged connections between elements such as nickel and hypothetical engineering solutions, sparking lively debates among enthusiasts and experts alike. These ideas are often fueled by articles, reports, or discussions on online platforms like Medium, where journalists and researchers frequently emphasize potential unusual aspects. One of the participants in these discussions, an esteemed scientist named Lowe, advocated for maintaining an open mind regarding hypotheses about the artificial origin of interstellar objects. His project, called the Galileo Project, was funded from private sources and aimed to search for technological signatures that could indicate artificial origins of such objects. This activity is entirely legal and falls within the scope of scientific research, even if some ideas involved are more speculative in nature. However, media coverage of these topics often exaggerates their significance and the likelihood of their realization, which raises concerns among critics. The scientific approach to these questions suggests that searching for signs of engineering solutions and technological signatures is only possible with confirmed data. For example, the detection of nickel in a cosmic object by itself does not indicate an artificial origin. Nickel is a common natural element found in various meteorites, asteroids, and other celestial bodies. Even if its abundance in an object is high, this does not necessarily mean the object is artificial. Naturally occurring dense objects can form without any human or extraterrestrial engineering activity. Therefore, to seriously hypothesize an artificial origin, one must have multiple independent lines of evidence supporting this claim. The null hypothesis, which should be accepted as the default and assumed until convincing evidence to the contrary is presented, is as follows. 3 specific objects, 3 asteroids and 1 comet, do not exhibit any unusual signals or signs of extraterrestrial civilization. In general, comets emit a broad spectrum of electromagnetic waves, with their radiation primarily consisting of thermal infrared light generated by the heated dust surrounding these celestial bodies. Additionally, they may emit some ultraviolet radiation and visible light, detectable by the human eye, due to the fluorescence of gases making up their composition. It is important to note that comets do not produce narrowband radio signals that could be detected and interpreted as signs of artificial origin. If no extraterrestrial signals are found during the search, this is a quite expected and natural outcome. Such a result by no means indicates that the technological capabilities for detecting extraterrestrial civilizations are absent. It merely suggests that current methods and equipment are insufficient to detect such signals if they exist. The lack of evidence is a weak but still significant indication, as thorough searching and data verification make the conclusion of complete absence more justified. However, this does not constitute definitive proof of the absence of extraterrestrial technology or signals, since absence of evidence under strict search conditions is not equivalent to evidence of absence. After conducting coordinated observations at specific times, organized through amateur radio communities and SETI groups, it becomes possible to more carefully test the hypothesis. During these times, specific dates and hours are chosen when the comet occupies a favorable geometric position relative to Earth, increasing the chances of detecting potential signals. An important condition is observing multiple objects simultaneously, along with subsequent analysis of the collected data to enable comparison and confirmation. The longer data is collected, the greater the chances of detecting a weak signal or ruling out coincidence. If someone claims to have detected a signal originating from the area corresponding to the comet's position, it is crucial for other researchers to verify these recordings, compare their own observations, and confirm the authenticity of the find. Such an approach helps build trust and increases the likelihood of the discovery being recognized. In science, a solitary detection of a suspicious signal is usually not considered conclusive evidence. Only repeated, independent confirmations obtained by different groups can constitute a significant discovery. Therefore, it is very important to precisely describe and record all details: sky coordinates, signal characteristics, its temporal structure, the presence or absence of polarization, as well as any signs of modulation or pulsation. The detected signal, if it indeed originates from the region where the comet is located, should exhibit certain characteristics. It should appear in those areas of the sky that correspond to the predicted ephemerides, calculated coordinates of the comet's position at the given time. Moreover, its radio signal should demonstrate a Doppler drift, meaning a change in frequency due to the comet's movement relative to Earth. This indicates the presence of a relativistic shift, which can be calculated knowing the orbital parameters. It is also important to consider the degree of polarization of the signal. An artificial source is likely to have a specific polarization or none at all, serving as one of the signs of its possible artificial origin. The temporal structure of the signal also plays a key role. It may be pulsating, modulated, or have a complex temporal dynamic, whereas constant, monotonous carrier waves, though possible, are less likely in the case of an artificial source. If the signal contains encoded information, this would be a definitive argument in favor of its artificial origin. However, decoding such information is a complex task requiring additional efforts and analysis methods. Overall, when searching for and interpreting such signals, it is crucial to consider the possibility of their artificial origin and subject all detections to rigorous verification. Looking for such objects, listening for them, and studying them are all important. However, one must not blindly believe everything seen or heard without solid evidence. This is the main principle of the scientific approach. Before accepting any hypothesis or information as truth, a thorough verification must be conducted to confirm its authenticity. When new evidence or proof appears, it is wise to subject them to the strictest analysis and testing to eliminate the possibility of errors or misconceptions. Only in this way can we avoid the trap of overconfidence and illusions that can easily arise in conditions of uncertainty. This approach helps us maintain critical thinking and resist deception or false expectations. Undoubtedly, in the modern world, full of mysteries and uncertainties, even without relying on beacons or extraterrestrial probes, discoveries such as the detection of 3 interstellar objects have changed our perspective on conversations related to extraterrestrial civilizations and cosmic secrets. These discoveries have prompted reflection and expanded the horizons of scientific and philosophical discussions. Let us consider the broader context, the consequences of these events for science and politics, because they influence our perception and preparation for the future. So, let us suppose that the 3 known interstellar objects are exactly what they seem: frozen visitors from another star system, passing through our solar system on their way back into the vast emptiness of space. Even if we accept as fact that these objects are indeed comets or similar bodies originating from beyond our solar system, this story still holds immense significance. These objects, quietly traveling through space without bright signals or signs of life, have already changed our perspective on interstellar science, how we operate our spacecraft, and how we communicate under conditions of uncertainty. The implications of such discoveries extend far beyond mere scientific curiosity. They influence how we respond to new data, emphasize the need for transparency in research, and demand the development of infrastructure capable of monitoring the skies. In this context, it is crucial to start with science itself. The 3 objects discovered over the past 8 years represent the 3rd confirmed case of an interstellar body, after Oumuamua, detected in 2017, and Borisov, identified in 2019. Thus, in 8 years, 3 such objects have been found, not as many as one might think, but enough to establish a certain pattern. This suggests that our galaxy is not empty, that there is movement within it, and that various chunks of rock and ice, ejected from forming planetary systems, drift through interstellar space. Current models estimate that thousands of such interstellar objects may be present in our galaxy, entering the inner solar system each year. Most of them are too small or too faint to detect, so we only see the tip of this distribution: large, bright bodies that happen to pass close enough to Earth or the Sun to attract our attention. The discovery of these 3 objects is the result of the work of the Near-Earth Object Warning System, known as ATLAS, or the Ground-Based Object Observation System. This system is a network of automated ground-based telescopes designed to search for near-Earth asteroids and other potentially hazardous objects that could threaten our planet. It scans the sky every night, constantly searching for moving objects to detect them early and assess potential risks. When one such object, as in the case of Oumuamua, was discovered, it was already approaching our planetary system, passing beyond Jupiter's orbit. If this object had been smaller or if its trajectory had been different, we might have completely missed its appearance, failing to notice or warn about the potential threat. This fact speaks volumes about our capabilities and limitations in observation. It underscores the importance and necessity of investing in various sky surveys, including projects such as the Atlas, the Zwicky Transient Facility, panoramic star maps, and ultimately the Vera Rubin Observatory, which is expected to begin operations in the coming years. These initiatives enable continuous monitoring of the surrounding space environment, expanding our knowledge of celestial objects and processes. Rubin, the person who will lead this project, will become an active participant in observations. His task will be to map the entire visible sky every few nights. This will require the use of highly sensitive cameras capable of detecting objects much fainter than those identified by current surveys. Such sensitivity will allow us to detect even the weakest and most distant objects. If interstellar bodies are as common as modern models suggest, then dozens, possibly hundreds, of such objects could appear on his observational horizon over the course of his work. This would mean a shift from rare studies aimed at gathering small statistical samples to more extensive and systematic research. Through these observations, we can find answers to crucial questions. For example, what do typical interstellar objects look like in terms of structure and composition? Do they resemble solar system bodies such as comets and asteroids? Or might we discover exotic types that have remained invisible to us until now? How frequently do these objects appear from specific directions within our galaxy? Do they follow preferred trajectories? And what can their properties tell us about the structure of the interstellar medium, as well as the locations of nearby star-forming regions? The three largest surveys, even without revealing all their secrets, are already teaching us important lessons. They demonstrate how vital the frequency of such surveys is, the need for rapid orbit determination of interstellar objects, and the importance of coordinated actions when detecting objects across different wavelengths of the electromagnetic spectrum. In July of this year, the Hubble Space Telescope was launched into orbit and began monitoring. Then, in August and September, ground-based telescopes followed, tracking and refining the parameters of the detected object. In early October, orbital spacecraft around Mars attempted to conduct observations. This is an example of a multi-platform campaign that combines space-based and planetary instruments. Such coordinated activity proves the concept that, upon the appearance of an interstellar object, we can quickly mobilize all available resources to study it. However, this situation has also revealed existing gaps. During the Martian observation window, ground-based telescopes faced limitations due to the comet's low solar elongation, which placed it too close to the Sun in the sky, making tracking difficult. At the same time, orbiting spacecraft around Mars had suitable geometric conditions for observation, but their primary focus was on planetary objects rather than comets or interstellar bodies. Visualizing a distant comet is more of a pleasant bonus than a main objective of such missions. This experience highlights the need for future design and planning of specialized operations and missions focused on rapid response. If, in the future, the number of interstellar objects increases significantly, which is quite likely, it would be prudent to consider creating a system of quick response capabilities for our observational missions. For example, orbiters around Mars could be equipped with small broadband spectrometers or cameras specifically designed to capture fast-moving objects. Similarly, telescopes in near-Earth orbit could reserve certain discrete time slots to instantly begin observations when sudden interstellar objects appear. Here is a list of the tools we currently have. This observation plan must be executed within 24 hours. During this time, no committee meetings, proposal writing, or recommendations are planned, just follow your route. At one point, the Martian window for 3 spacecraft known as the Atlas was illustrated by demonstrating how important it is to be able to see what is happening from multiple points simultaneously. When Earth could not provide observation, Mars could serve as an alternative, given its spatial advantage in this situation. In the future, we have the opportunity to expand our assets further, continuing observation and data collection. For example, the SOAP mission is a research spacecraft sent to Jupiter's icy moon, currently en route to Jupiter and expected to arrive around the year 1031 AD. There is also the Psyche mission, heading toward an asteroid located in the belt between Mars and Jupiter. If an interstellar object passes through our system via the outer solar system, such missions could provide valuable information that surpasses ground-based telescopes' capabilities. The same approach applies to interstellar probe missions, which we have discussed in the context of science fiction. If one day we decide to send a probe to another star, it could serve as an early warning system for interstellar objects moving toward our system. Although the probability of this is low, it is worth considering. Now, let's talk about transparency and communication. In situations where infrastructure is shut down or disconnected, regardless of what exactly you understand by that, an obvious weakness has been revealed. NASA, speaking to the public, faces a situation where their communication resources are cut off at the moment of an important scientific event. Their own continuity plan clearly states that communication should be maintained during such times. However, in practice, during periods of funding gaps or technical failures, the public loses access to NASA's official websites, social media accounts, and even television broadcasts. This is an organizational policy, not a conspiracy. Nevertheless, this approach creates a negative perception. An information vacuum arises, and as is well known, vacuums tend to be filled with rumors and speculation. Many assume that silence indicates the concealment of some important information, despite the fact that often the reason is simply bureaucratic procedures or technical issues. At the same time, the European Space Agency continued to publish updates about their plans and issued official statements regarding their spacecraft, such as Mars Express and the observation of gas traces on the ExoMars orbiter. This asymmetry in behavior between the two leading space agencies, NASA's quiet and closed stance versus ESA's active communication, made the situation with the disconnection more noticeable and perhaps even more suspicious than it actually is. As a result, assumptions are made that the events are being hidden or controlled to conceal some critical information. This, in turn, fuels conspiracy theories that have long been prepared and circulated among those inclined to such hypotheses. They expect that there is some hidden secret surrounding interstellar objects and similar anomalies, and that this is the reason for secrecy. From this, an important conclusion can be drawn. Transparency during the emergence of anomalies, unforeseen events, or disconnections is not an option but an absolute necessity. Maintaining public trust is directly linked to openness and honesty in communication. Even if the only message is that observations are ongoing, data is being collected and analyzed, and results will be published as soon as communication can be restored. That is far better than complete silence. Silence breeds doubt, arouses suspicion, and sometimes fuels rumors. Future situations involving disconnections and shutdowns should be proactively prepared with contingency plans. Space agencies must seriously consider this issue, as the situation that may arise upon discovering an interstellar object is truly unusual and requires special attention. Imagine a situation. We suddenly come across something that doesn't look like an ordinary space rock or comet, but rather appears to be of artificial origin, or something that could pose a threat to our planet. In such cases, many questions arise. Who exactly decides when and how to announce such a discovery? And how is the communication chain structured if standard channels are temporarily unavailable or not functioning? This is not purely a hypothetical scenario, and the questions are only increasing. Let's take, for example, an organization that collects and processes data. Let's call it Atlas. No matter what the object is, ordinary or strange, it must be prepared for rapid response. Currently, data processing policies at space agencies are essentially systems prone to delays. Most planetary mission data are published in batches, often with a delay of several months or even years after collection. This is standard practice that works well for routine research and long-term projects. Scientific teams are granted the right to use the data for a certain period, after which it is transferred to public archives accessible to the entire scientific community. This approach is excellent for studying stable phenomena and constant objects but is completely unsuitable for fast-paced, unpredictable events such as the appearance of interstellar objects. As data are collected and go through all necessary checks and processing, the object may have already disappeared or changed position by the time the information reaches the wider audience. The time required for official publication is often too long, and by then, the event has already lost its relevance. Therefore, to respond promptly to such phenomena, a more flexible and faster data transmission system must be implemented. An optimal model would involve providing raw data in real-time or near real-time about the most priority targets. That is, images and spectra obtained within days of detection, even if they are not yet calibrated or contain noise and interference, should be accessible to the scientific community. This would allow specialists and enthusiasts to immediately begin analysis, search for anomalies, and note unusual features. Such crowdsourcing, collective participation of many researchers and amateurs, can identify unusual characteristics much faster than if data were processed only within limited teams working on a single mission. If the detected anomaly proves to be genuinely interesting or dangerous, the community can react quickly, and in the absence of threats, continue research and monitoring. There is no need to wait for official reports or comprehensive publications, which often take a lot of time. As a result, the risk of missing important information or failing to coordinate subsequent observations in a timely manner is significantly reduced. It is also important to emphasize that this approach minimizes the risk of premature disclosure of information, as data are published immediately without delays associated with bureaucratic procedures. At the same time, there is a counterpoint: the risk that the data could be misinterpreted or misused. However, considering that we are dealing with emergencies or anomalies, the advantages of rapid information exchange outweigh the drawbacks. When it comes to the international level, such coordination has already taken place during Mars missions, which gives hope. On the European side, for example, cooperation demonstrates that united efforts can achieve significant results. And if in the future interstellar objects become more frequent, we will need to establish a permanent international structure capable of promptly coordinating observations worldwide. Imagine a system similar to the International Astronomers' Union for comets and asteroids, expanded to include interstellar objects. This network would include space agencies, ground-based observatories, and amateur astronomers, all connected on a single platform where data are shared and processed collectively. Upon discovering a new interstellar object, this network would activate automatically. The area of study and commercial activities related to asteroid mining have long been subjects of active discussion and scientific debate. These ideas arise in the context of exploring not only our nearest cosmic neighbors, such as asteroids, but also extend to more mysterious and complex objects beyond the solar system, interstellar bodies. They add a particular urgency to these considerations because they move at high speeds, meaning that the opportunity to intercept and study them requires special efforts and strategies. The response time to the appearance of interstellar objects is very limited. Researchers and engineers have only a short window to detect, record, and collect samples from such bodies. The delta V required to achieve these goals is extremely high, and currently, using existing rocket propulsion systems is often impractical. Modern propulsion units simply cannot develop the rapid acceleration needed to intercept such fast-moving objects. However, if it were possible to overcome these technological limitations, the scientific opportunities that would open up for humanity would be truly enormous. Imagine a sample of material from another star system delivered to Earth's orbit. This would be more valuable than any meteorite ever found and studied. Such a specimen would allow us to uncover the secrets of alien planets, star systems, and possibly even new chemical elements or structures previously inaccessible for research under Earth conditions. At the same time, the legal aspects of this issue remain quite vague and complex. International space law, particularly the so-called Outer Space Treaty, states that no country can claim sovereignty over celestial bodies, whether planets, asteroids, or other objects. This creates a certain legal uncertainty regarding the rights to extract resources beyond Earth. However, despite these restrictions, there is no full certainty that such limitations can completely halt initiatives or prevent the development of similar programs. After all, the extraction and utilization of resources from celestial bodies is a matter that provokes considerable debate and disagreement, as there is ambiguity in the legal framework concerning the rights and obligations of the parties involved. The situation with interstellar objects is especially complicated because they do not belong to any specific system or country. These objects are in the most ambiguous zone. They are not part of any one solar system but rather pass by it, moving through space at speeds exceeding all usual indicators. If it were suddenly possible to intercept such an object, the question arises: can it be preserved and used? Probably yes, although with many technical and ethical nuances. At the same time, the question is raised: what will society and the global community say about this? What moral norms and values should guide us in relation to such interstellar visitors? Planning future missions to study interstellar objects does not necessarily require fantastic or exotic technologies. There are quite accessible tools for detecting, tracking, and studying such bodies. For example, wide-angle cameras, spectrometers designed to determine the chemical composition of objects, photometers that monitor brightness changes and help identify their nature, as well as radars, all are available in the arsenal of modern spacecraft. Their use is not particularly difficult if work is properly planned and rapid response to new targets is ensured. In this regard, existing technologies and means already exist. Orbital satellites, located on Earth or near planets, could perform such tasks tomorrow if they had sufficient flexibility in management and the ability to quickly switch between tasks. But the main question here is not the availability of technologies or tools. Cultural and organizational preparation, internal understanding, and recognition that interstellar objects are not rare phenomena but rather quite common and potentially significant objects are essential to justify the development of specialized programs and missions from the very beginning. This marks the key shift in approach. We must understand that searching for and studying interstellar objects requires more than just curiosity, it demands a comprehensive effort. The galaxy is incredibly rich with mysteries, and our scientific research and observations become more advanced and precise with each passing year. In this context, if ever an astronomical phenomenon appears that goes beyond conventional understanding, if we suddenly encounter an event that by its nature resembles not just an ordinary comet or meteor shower, but something truly unique and previously unseen, then the entire existing infrastructure, all the achievements of modern science, and international cooperation will be necessary to study it. Transparency and openness are essential to understand what exactly is hidden behind this phenomenon and to collaboratively uncover its secrets. The question is not whether we will discover something unusual, because the answer to that is likely obvious. We will definitely find something. The real question is how prepared we will be for what awaits us when that happens. It is also important to realize that the research process will not end instantly, even if we reach a certain stage of understanding. We are approaching the end, or at least the final point, of this particular yet still not fully revealed secret, because the story related to TriAi Atlas is not over. This narrative is only temporarily paused, as if waiting for the moment when the light will be reignited to continue what was begun. There is a part 15 in this story. It is a synthesis, open endings, and promises yet to be fulfilled. Therefore, let us gather our strength to prepare for what lies ahead, because the night, according to plans, will fall on the 1st October night of 2025. At that moment, the American government will cease its operations, and a few hours later, the entry into orbit around Mars will occur. This is not just a coincidence but perhaps a sign or even a cover-up. You are here to answer important questions. I will prepare my response for you, but it will not be simple and cannot fully satisfy everyone. However, as you analyze all the data, noises, and clues, it will become clear that both versions of events, the communication blackout and silence, may be true simultaneously. The disconnection was indeed related to a procedure followed to ensure safety. Yet, it was precisely this silence that created conditions in which something unusual could either be underestimated or delayed, which may have been important. The essence of the entire story lies in this ambiguity. Let's start with the facts to better understand the situation. First, it is necessary to note that NASA was closed to the public during this period. According to the plan they published themselves, activities during this temporary funding and resource suspension are completely halted. Public communications cease, all information sources are shut down, websites go dark, news disappears, NASA's television is turned off, and social media accounts are frozen. The only operations that continue are those directly related to life and property protection, namely supporting the operation of the International Space Station, managing ground-based satellite control centers that may malfunction or experience disruptions, and critical safety measures for the Artemis program. This category also includes Martian orbiters designed for reconnaissance and research. For example, the Mars Reconnaissance Orbiter, MAVEN, is expensive equipment built to operate in the harsh conditions of the Red Planet. These spacecraft are not allowed to be endangered, as they perform vital tasks. During this time, flights continued, teams were dispatched, data was collected, and although there was no public announcement, all activities were confirmed within the professional community. In other words, despite the absence of official statements and publications, information gathering efforts persisted. What did not continue was public coverage of the events. There were no press releases, daily posts, or tweets, unlike the usual coverage of such missions. This gap in information exchange is exactly what everyone noticed and felt. It significantly complicates the support of any conspiracy theory suggesting that something unusual or important occurred in our solar system and was concealed from the public. After all, if such an event, capable of fundamentally changing our worldview, had truly taken place, observers monitoring space, such as international astronomical organizations, would have definitely recorded it. primarily, the International Astronomical Union, IAU, as one of the most authoritative and responsible bodies, would not have overlooked such information. If such an event had occurred, it would have been documented and published in open sources so that all interested parties could study it and verify its reality. It is worth noting that perihelion, the point in the orbit of a comet or other celestial body closest to the Sun, is a very significant astronomical event. In the case of the comet known as Trigger, its perihelion occurred around October 29 or 30, 2025. This is a special moment when the comet was at its closest approach to the solar star, approximately 1/36th of an astronomical unit inside Earth's orbit. Compared to Earth's orbit, this is not very far, but still far enough that such an event would remain invisible to the naked eye, considering lighting conditions and distances. After the comet reached perihelion, it began to swing outward, meaning it moved back along its orbit and eventually passed behind the Sun. At least, this is how it appears from the perspective of an observer on Earth. At this moment, Earth, moving along its orbital trajectory, enters a solar conjunction with this cosmic visitor. During the solar conjunction, when Earth is directly between the Sun and the comet, it becomes impossible to observe it. The bright sunlight interferes with the view, causing the object to disappear from our planet's field of vision. This period of invisibility, the time when the comet is hidden behind the bright light of the Sun, lasts for most of November. At the end of November, or possibly at the beginning of December, the comet will reappear on the opposite side of the Sun, sufficiently distant for ground-based telescopes to detect and record it again. This will provide a unique opportunity for observers and astronomers to gather new data about its characteristics, trajectory, and composition. When the comet becomes visible again, a window will open for new observations and studies that could shed light on many questions related to this celestial object. At the time of writing this scenario, that is, in early October, we find ourselves in an intermediate situation, in some uncertain period of time. A time when observations of Mars were either being conducted or only planned, depending on the agency or organization involved. It is important to emphasize that the data from these observations have not yet been published, and no detailed reports have been made about them. This was expected. Publications of results from Mars missions are often delayed, sometimes by several weeks, and sometimes even by months. Such delays are due to the need for careful data processing, verification of the obtained information, and preparation for publication. Although the spacecraft exploring Mars continue their work without interruption, the people responsible for processing and interpreting the data face various bureaucratic and technical delays. These delays only increase uncertainty and add further difficulties in understanding what is happening. While the spacecraft continue to carry out their missions and collect valuable data, the specialists working with them encounter delays in data processing, which often leads to frustration and disappointment. As a result, publications from Martian stations are usually delayed by several weeks or even months, making it harder to receive and analyze new facts in a timely manner. The perihelion passage is an event happening right now, at this very moment. At the same time, a large-scale event is beginning. They simply publish numerical values without immediately trying to explain their meaning or origin. If these numbers are taken from several independent sources, such as different observatories located around the world, agreement between them becomes an important and convincing indication that the orbit of the object is indeed changing. Such a level of consistency suggests that the motion modeling has been carried out correctly and accurately. At the same time, if the data obtained diverge from each other or if unexplained residual phenomena are observed that do not fit into existing models and cannot be explained, this serves as a warning sign, often referred to as a red flag in scientific practice. The next important step is to observe Mars using the European Space Station and the mission page where fresh images and updates are posted. The European Space Agency generally approaches the publication of new images and information very carefully and cautiously. It regularly publishes visual materials and updates the status of its spacecraft, allowing for the tracking of any changes. If spacecraft such as Mars Express or the Trace Gas Orbiter detect anything interesting, be it new activity, unusual phenomena, or surface condition changes, all this data will eventually appear in public sources. Perhaps not immediately, perhaps after some analysis, but raw images, spectra, or other unprocessed data will inevitably surface, as space probes collect vast amounts of information. When these materials become available, they need to be compared with expected results. First of all, it is necessary to check the timestamps. Do they match the scheduled observation windows? It should be verified that the data correspond to the predicted brightness of the object and its movement. If all indicators align and proceed as planned, one can conclude that the situation is developing according to predictions, and the explanation for what is happening is the simplest and most justified. However, if inconsistencies or deviations are discovered, this raises more complex and interesting questions that require further analysis and explanation. Third, it is essential to closely monitor NASA's publications and data, especially after the regular release of information related to missions ceases. When a particular phase of work ends or funding is halted, the space agency team begins publishing reports on accumulated data volumes and research results. There is a dedicated page, for example on nasa.gov, where recent updates are posted. These include observations made by the Hubble and James Webb telescopes, as well as any mentions of Mars missions, such as reconnaissance orbiters or the MAVEN mission. If such observations took place, their metadata, timestamps, instrument modes, target coordinates, are definitely available. Even if a complete analysis has not yet been finalized, data logs and metadata should be available. The absence of such documents or gaps in the timeline, especially during periods when specific equipment shutdowns or stoppages were expected, is unusual and concerning. While this is not direct evidence of any anomalies or secret events, such irregularities warrant special attention and further investigation. An important aspect to monitor is the tracking of scientific publications related to the topic of interest. For example, in July of this year, a preprint related to research that could be relevant to the situation was published on the Hubble preprint platform. If articles appear in scientific journals containing new data or results connected to the observation window of Mars, they should be carefully examined. First and foremost, pay attention to the list of authors to understand who is behind the research and who is funding it. Focus on the confirmations presented in the articles. What instruments were used? What methods and analyses were conducted? Articles undergo peer review, and reviewers thoroughly verify the credibility of the data presented. If irregularities or inconsistencies are found in the data, they will either be identified and discussed within the scientific community or become the subject of further investigation. Ultimately, the scientific process is slow. It may sometimes seem clumsy, but it is essential. When observing a comet that appears quite normal at first glance, with brightness developing according to preliminary predictions and its coma behaving as expected, all of this serves as strong evidence that we are likely dealing with a simple, familiar comet. In such cases, it is clear that the object is indeed a comet, and no extraordinary or unusual phenomena are expected. However, as soon as something goes beyond these expectations, for example, if the comet's brightness is significantly higher or lower than predicted, or if its emission spectrum shows unusual lines, this is the moment when attentive observers start to notice and speak about it loudly. Such deviations attract attention and generate interest within the scientific community and among enthusiasts, as they may indicate something unusual or even mysterious. In addition to these observations, it is important to coordinate efforts and, if possible, share your results with others. In previous sections, it was mentioned that amateur radio telescopes could become a useful tool in the search for possible artificial signals originating from space objects. I am not overly optimistic about success in this area, but the very fact that such an opportunity exists and that the tools are accessible to the general public makes the attempt quite justified. If you have access to software-defined radio and a good antenna, you can record the dynamic spectrum by pointing it at a specific point in the sky, for example, the area where a comet is located, and track it during the window of its reappearance. Equally important is to use GPS timestamping when recording data, so that results can be accurately correlated with similar data from other observers, significantly enhancing the reliability of the analysis. For data processing and analysis, it is recommended to use open-source software such as New Radio or SDR Sharp. This allows recordings to be saved in formats that are easy for other researchers to open and analyze, promoting transparency and collaborative work. Moreover, it would be very valuable to share raw data with the community. Because if 5 people in 5 different countries record the same signal on the same frequency and observe converging parameters, such as the Doppler drift corresponding to the comet's movement, it would constitute a real scientific breakthrough. Such an event could even be a reason to receive a Nobel Prize, as it would be extraordinary and unique. However, the reality is that such an occurrence is unlikely and almost certainly will not happen. These events are very rare, and the probability of their happening is extremely low. But the important fact that anyone interested can try, given that the tools are available and information is freely accessible, is already a significant step forward. This means that the search for such signals is not limited by any closed systems or paid services. It is democratic, open, and accessible to everyone with the appropriate equipment and desire. Now, let's consider the possible hypotheses explaining the unusual phenomena associated with the comet. The first hypothesis is a bureaucratic coincidence. Perhaps the suspension or interruption of observations was simply a temporary measure caused by internal necessity, whether related to funding rules or internal regulations. Either way, it was just a temporary halt. Public communications from NASA regarding this event were suspended precisely due to rules related to funding and internal policies, while all necessary data was collected as usual. The research results are expected to be published according to the planned standard timelines, making this version of events the most plausible and credible. There is no need to introduce complex assumptions or suggest hidden motives. It is based on known facts and does not require any conspiracy theories or information concealment. The whole situation may seem dull, but often the most mundane explanations turn out to be the correct ones and align with reality. If we consider the hypothesis of falsification, that is, the possibility of deliberate data distortion, the situation becomes more complicated. For example, the comet has an unusually high mass and density, which at first glance might suggest an internal structure rich in metallic components. It is quite possible that this celestial body has a core made of metals, consistent with some planetary models. However, all of this remains speculative, based on indirect data and hypothetical scenarios. For instance, there is a possibility that the comet could have ejected fragments of its core into interstellar space, as well as nickel emissions recorded in several observations. These emissions and mass estimates, derived from images obtained by space telescopes such as Hubble, are at the upper limits of acceptable ranges, raising certain doubts and requiring critical analysis. Nevertheless, it is important to emphasize that such assumptions are nothing more than guesses, as current data do not provide definitive evidence supporting the metallic core hypothesis. If the size and albedo of the comet, measured through observations, along with mass and size constraints, indicate a small core, and spectroscopy shows the presence of common cometary volatile substances, water vapor, carbon dioxide, and others, then the hypothesis of a metallic core loses its relevance and cannot withstand scrutiny. In other words, if the spectra show a standard composition, and the size and albedo correspond to a typical comet, then the assumption of a metal-containing core becomes increasingly unlikely. The next hypothesis involves the possibility of a so-called black budget, hidden data that could explain the object's unusual behavior. In this context, information obtained from the so-called Martian window, a time period when observations of Mars are most effective, exists. However, this data remains inaccessible to the general public because, apparently, it is either concealed or under the control of military or intelligence agencies. Assessing the true situation is difficult because all related information is, by definition, classified and unavailable for public review. At the same time, there is currently no evidence to confirm that such data actually exists or has been leaked. All existing information amounts to the absence of proof to the contrary. If such secret data did exist and were published, they would most likely contain timestamps and content consistent with unclassified observations. In the absence of such data, one can only say that the hypothesis of a hidden, black budget remains just a hypothesis based on a complete lack of evidence. In other words, if such information has never been published or made publicly available, this supports the hypothesis of its non-existence. However, it is important to consider that sometimes, due to technical reasons, observations may simply fail to detect relatively rare events, which does not disprove the hypothesis but only leaves it within the realm of speculation. The third hypothesis is related to the possible interference of third-party actors, both governmental and private organizations, who may have conducted a close flyby or data collection during a recent observation window of Mars. In this case, we are talking about a clandestine actor who could possess technologies capable of performing such operations. This hypothesis is considered the least confirmed, as it requires the existence of technologies far superior to current ones, as well as secret agreements and hidden motives, making it highly speculative. It is also necessary to consider that falsification of these data is a very likely possibility, because if the observed objects and processes were the result of interference, signs of this should appear in orbital and ground-based observations, anomalies, unusual emissions, traces of interference. However, numerous independent observations, including orbital and ground-based, have revealed no signs of anomalies or emissions, which significantly reduces the likelihood of such a scenario. The fourth hypothesis relates to the possible technical or engineering origin of the object. That is, the assumption that it is not a natural body but an artificial artifact. For example, it could be an abandoned craft. This is how one should approach any mystery related to unknown or incomprehensible phenomena. First and foremost, it is necessary to start with the simplest explanation for any mystery or unusual situation. One should not immediately resort to complex and large-scale investigations until simple explanations have been thoroughly exhausted and proven incapable of providing a clear answer. Transition to more complex levels only when everything that can be explained with simple means and observations has been checked and yields no results. So, what exactly do modern technologies and scientific methods promise us? What commitments and principles am I personally ready to undertake in the pursuit of truth, and what commitments do I ask you to observe? When new data appear, when documents are published, when images are posted, at that very moment, we return to questions, analyze, and verify all received information. First and foremost, we begin by checking receipts confirming data receipt. For example, NASA published an image from a high altitude or perhaps a Martian image that represents a tiny fragment of a reconnaissance orbiter or its parts in the Martian window. If so, what exactly do these images show? Is there something unusual or anomalous in them? Or is the image blurry and behaving like a comet or some luminous spot, raising questions? Next, when the European Space Agency, ESA, publishes data from its satellites, such as HRSC or CASI, we verify whether this data aligns with our forecasts and expectations. Are there brightness peaks, spectral anomalies, or anything unusual for typical space objects on these images? Do unexpected spectral surprises occur, or are there signs that shouldn't be present? The Small Planet Research Center updates its orbital solutions using new, post-perihelion data. If so, we compare whether the residual errors have decreased or, conversely, increased. Do these data show signs of non-gravitational forces that could influence the object's trajectory or appearance? Most importantly, are these parameters internally consistent and coherent with each other, ruling out effects like outgassing or other unexpected phenomena? We go through this checklist item by item. We compare what was promised with what has actually been achieved. We note discrepancies, identify confirmations, and adjust our confidence in the received information. If all points are fulfilled and match, then the mystery was mainly due to our misperception, poor timing of observations, or communication issues. In such cases, the problem is more likely in our minds than in the situation itself. But if gaps, contradictions, or data that do not fit together are found, then the mystery becomes real and requires deeper investigation and analysis. We ask more complex questions, demanding more precise and justified answers. And for this, there is no need for a doctorate-level knowledge or access to secret briefings. Patience, a desire to understand, and the right tools are all that matter. You will need a browser to compare timestamps with the calendar, check whether the data was published on time, and whether it matches our forecasts. All of this are accessible and open tools for verifying information. Use them without fear or doubt. And finally, the last thought: what should remain with you after this journey into the world of mysteries and data? If a certain object, for example, a hypothetical 3I Atlas, was created as an artificial probe, relay, or even a fragment of ancient extraterrestrial infrastructure, it would not quietly and unnoticed hide in the pixels of a database. Such an object would definitely leave its trace, a trace that could be detected through analysis of telescope data across the entire spectrum, over months and years of observations. This trace would manifest in astrometry, photometry, and spectroscopy. It would appear in ways that cannot be explained simply by the presence of ice or dust. This trace is what we are searching for and what represents our future. It would remain in the form of specific data and publications. Or continue to carefully observe the celestial sphere, never cease watching the stars and cosmic objects, and constantly double-check your sources of information, striving for the most accurate data. Keep asking questions, even those for which clear answers are hard to find, because such questions lead us to the truth. The entire universe, in its boundless wisdom, is not obliged to give us simple and understandable answers. It does not have to do so for us or anyone else. But if we persist, remain vigilant, and honestly acknowledge what we truly know and what remains a mystery, we will ultimately be able to find the truth, even in the most complex and tangled situations. That is our task, to not give up and to continue searching. When a comet orbits the Sun, gathering information and all data come to us, we will remain in anticipation, ready to piece everything together to understand what is happening. At such moments, each of us experiences an inner feeling: I am here, I am observing, and I am prepared for what will be revealed to us in the future. If I usually ended my story with the words, "See you next time," it is worth noting that the next time is already scheduled. It will likely occur at the end of November or the beginning of December, when the 3 Atlantes will come to the forefront due to the Sun, and telescopes will once again record new data. Then we will gather again to continue our exploration. It is precisely at that moment that answers will start to come to us. And even if they turn out to be boring, for example, just another comet, that is no reason for disappointment. Because the process of searching, investigating, and trying to understand what is happening is, in itself, an exciting part of science. It is that very mechanism that helps us distinguish important signals from noise, understand what truly matters, and what are just random interferences. This is where our honesty and scientific integrity lie. But if the answers turn out to be less predictable or dull, if even a single fragment of data, one measurement that does not fit our theories, or one signal that cannot be explained by existing models, all of this will mark the beginning of a new story. And you will definitely want to stay to see what happens next. Therefore, I advise you to mark important dates in your calendars in advance, keep an eye on information sources, download data as soon as it becomes available, and compare your records with those of other researchers doing the same. All of this will help assemble a complete picture from many individual parts, and over time, when we have enough details, we will be able to see the whole picture and understand it. When we reach the moment when we gather the necessary information, perhaps on the night at the end of October 2025, we will know the truth. Then we will find out whether the 3 Atlantes, this name used to refer to a mysterious comet or object, was truly a cosmic visitor or merely a calling card that left a trace behind. For now, the mystery hangs in the space between what we saw and what we had to overlook. It exists between what was said and what was silent, between coincidence and attempts to hide something important. This gap is the very uncertainty that lies at the heart of all our enigmas. In this space between the known and the unknown, the most vivid and captivating stories are born. And now, the lights in the distant cosmos begin to approach once again, returning to us to illuminate new horizons. Let us carefully observe what they will show us, what kind of light they will bring. The time to uncover new secrets has not yet passed, and right now, at this very moment, we have a unique opportunity to watch what is happening and prepare for new discoveries. The entire universe seems to invite us to a dialogue, and only through our persistence and honesty will it reveal some of its secrets, leaving others for next time.